Okay, hello there. Well, let's see. Today we're going to try doing something a bit different. Today, somebody had the idea that this should be Math Storytelling Day. So I will try and tell some stories about math. And I guess let me try and tell a little bit of the story of math, starting at the very beginning. So we might start off with kind of what is math? Math is kind of a system of abstraction about the world. It's a little bit like back in the day before human language was invented. Maybe one could imagine people were just like pointing at things to say, that's what I mean, and so on. And then eventually this idea emerged that there could be a word, like it's a rock, it's a mammoth, it's whatever, an abstract word that could describe a mammoth, any mammoth. That's kind of a system of abstraction that is our version of human language. And there are other systems of abstraction like logic and so on. And a really big one that is the one I've spent my life working on is computation and the idea of following arbitrary kind of computational rules. But we're here to talk about math. So let's talk about the kind of abstraction of the world that is math. And specifically, math tends to deal with abstractions that involve things like numbers and shapes and space and so on. Okay, so let's start off with kind of where did things like numbers come from? Things that we have today, they all had to get invented somewhere. You might say, aren't numbers just totally obvious? Isn't how could you ever be in a world without numbers? People say that there are, indigenous tribes in the Amazon jungle and places like that who don't have words in their languages for numbers larger than essentially 3. How can that be? Well, if you're hanging out with a group of people, and then you would typically say, well, I'm hanging out with John and Jane and Mary and Peter and so on. Each person has a name. You don't necessarily say, I'm hanging out with 7 people. You don't need to collectivize. You don't need to abstract the idea of number. Each person has a specific name. Okay, let's say you're keeping goats. You give each goat a name. Every goat is different. The goats aren't identical, but you might decide one day, perhaps because you start doing commerce and you're trading and you say, I'm going to exchange, 5 goats for 7 sheep or something like this. And then you've got to be talking collectively about the goats, collectively about the sheep. And for that, you start needing the idea of numbers. And the notion that you should just count the sheep and not just talk about every sheep as an independent individual sheep, that's kind of the key idea that leads to the notion of numbers. And so we don't know when that was first invented, but certainly from tens of thousands of years ago, there are examples of tally sticks where people would mark off, kind of make a series of marks, and maybe they were counting something. Maybe they were counting, the number of mammoths they saw that day or some such other thing. So then the question comes about, so how do you start off? You've got this idea of numbers. How do you represent numbers? And I suppose, and now let's actually go modern and computational here. Let's say we're going to represent a number, and our sort of first approach to doing that is to just say we're going to have we're going to say we're going to represent the number I don't know, 13 or something here, and and so we might do that by just having a bunch of a bunch of things marked off on our stick. I happen to write them as ones here, but I could as well have just written them as little marks on a stick. Well, if we've got, let's say, 5 marks, most of us can immediately say, oh, we kind of get the idea that's 5. We can compare it with this. There's more there, and so on. But one of the things we might want to do is to find sort of a more organized way to represent numbers than just having to mark off 1 mark for we're representing a number just by that number of marks, so to speak. So in terms of sort of the language of mathematics, one could say that writing a number this way is writing it in unary, in essentially base 1. But so a typical thing people do when they mark things off, you know, when they're checking things off on some piece of paper or something, is they might say, and again, I'm just using, I'm just doing this to as a way. Okay, they might mark off every time they get to 5 tally marks. They might sort of group those together and put a slash through them or something like this. And so then we can there, it's a little bit easier for us to see, okay, there are 2 groups of 5 and then there's 3 left over. You know, we have 10 fingers, so we have a habit of doing things like saying of grouping things in groups of 10. So we might say, here we go. We've got something where we've got our number. It's what we would call 43, but we've got 4 groups of 10 and then 3 ones left over. Okay, so this then the question is, how does one start to represent numbers? This is sort of the beginning of an approach to making numbers a little bit easier to deal with, is not to have to take sort of each one on its own, so to speak. Well, historically, there were a bunch of different methods developed. I think, let's see if we can pull one up here. Let's see, let's try this. Let's try something like 53 in, let's try something like Babylonian. This was an early number system. Let's see if this works. Wake up, wake up. Okay, maybe I should make this a little bigger here. Okay, so that's the Babylonian for 53, and I guess we can see 5 little marks of this kind and 3 little marks of that kind. If we go and say, let's do 78, okay, we're seeing slightly different markings because that mark there, I don't know, I'm guessing that, oh yeah, that mark there represented 60, that mark there represented 10, and then we got 8 left over. And in the Babylonian system, I think if we try and go to 128, for example, we'll probably get 2 marks for 60 and 8 marks for 1 there. So this was kind of a notation where you have something that means, oh no, actually this is just showing the 60 is off in this corner, and this thing here, I guess, is a 10. I'm guessing if we go back down here, well, we can, let's just use some technology here. Let's just make a list of Babylonian numbers from 1 to, let's say, 25. Okay, there we go. So 1, 2, 3, 4, 5, 6. Okay, so, and this, I guess, is the mark for 10. That's the mark for 11, and so on. And so here we're essentially just doing the same kind of thing that we did up here, except that we have we're using this mark to indicate a whole block of size 10 here. Well, there were other systems people used. So, for example, another one that was used was the Greek number system. Let's see what that one looks like. Okay, let's look for some smaller numbers there. Let's do the same thing for Greek. Let's say here. Okay, so here's the Greek number system, and the Greeks kind of had an interesting idea, but it ended up kind of being a goofy idea in the end, which was they said, well, we already have something which is in sequence, which is the letters of our alphabet: alpha, beta, gamma, delta, epsilon. Well, that's funny because that's not a letter. That, I think, is a digamma, which is not a letter that's in the standard Greek alphabet. And there's eta, theta, iota, and then here, I guess they're using for that's iota is kind of the symbol for 10, and then they're using these 10s again. But one of the things they did here was they said, let's just use the letters of our alphabet to represent successive numbers, which might have seemed a good idea at the time, but when letters of the alphabet kind of went out of circulation, that probably made it really confusing. Well, then the next kind of another number system is the Roman number system, Roman numerals. If we look at that, it had another scheme for representing things where we've got 1, 2, 3, and then 5 is an important thing. So we represent a 5 with a V, and then the 4 is represented by saying, well, it's 1 less than the 5, and so on. And so this is, if we keep going here up to 100 or something, we can see this whole system for dealing with Roman numerals, which no doubt was quite convenient when you just sort of glanced at a number. It was certainly a lot easier to tell what was going on where you saw XXVI than if you saw a bunch of tally marks or something like this. But when it came to doing things like manipulating numbers, adding them together, this was not an easy system to do that in. But so the sort of the big idea that, so the Roman numeral system was the one that was used for many years, actually, basically in the Western world until the 1200s. But there was this sort of alternative idea, the Hindu-Arabic system of numbers, which is the one that got brought to the West around 1200 by folks like Fibonacci. That had kind of a different idea. And its idea was to say, well, let's take these things where we have these blocks, and let's just say we're going to use the position of a digit to represent things. So here we're saying, well, there are 3 separated ones. We'll just put a 3-digit there. And here there are 4 blocks of 10. So we'll put a 4-digit to the left of that to indicate that there are 4 blocks of 10 here. And if we were to, let's say we were to do something like this, we were to say, I'm not sure I can quite, let's say we do 143 here, then the idea would be, we would then, let's try and do this. We could partition this again in groups of up to 10. Let's see if this works. Never tried this before, as a way to explain numbers. Okay, so now it's a little hard to see what's going on here. Maybe if we put, let's do this. Let's map frame onto this at framed onto it. So I'm using obviously computational kinds of things to do this. Okay, here we go. Maybe we want to go down to level 3 there. Okay, so here we've got, we're beginning to have sort of a different number system where we've got, we can see these sort of big mega blocks. I should have probably gone even further. Let me just try doing this. I wonder whether this will work. Let's see whether this works. Now we get the same thing. Okay, so what we're seeing is the individual ones down here. Then we're seeing these blocks of 10, and then we're seeing every block of 10, every 10 blocks of 10 is being separated off in another big block here. And so this is a way of thinking about kind of our positional number system where we say there's one block of 10 tens or one block of 100 there. We put down a 1 there. There's then 4 blocks of 10, and then there's 3 individual ones here. And so that's how we get kind of this positional notation for this number 143. And so that's kind of the, and this is then a way of representing numbers where we can represent even pretty big numbers. I mean, if we try and use, for example, let's try and use the Babylonian number system. Let's see how far it can go. Let's try representing the number, let's try just representing the number 1,000,000 in the Babylonian number system. I don't know whether it'll have a symbol for that. Okay, we managed to make it to 1,000,000. All right, let's live even more dangerously. Let's try and go to 10 million. Okay, well, we got some funky things showing up there. Let's go to 100 million. Still thinks it can do it. Maybe this one can be extended. That's interesting. I bet if we try and do this in the Greek number system, it will just give up. It only supports numbers up to 10,000. So we can go down here. Let's look at the number 9,000 in the Greek number system. Okay, I think what has happened here is that to represent, let's look at what happens at 900. Okay, that's the symbol for 900. I'll tell you what, let's look at, let's go look at all the numbers from, let's say we want to go up in hundreds. So let's just go 100 there. I goes from 100 to 1,000 in steps of 100. Okay, well, so they're just using other letters of their alphabet: rho, sigma, tau, epsilon, phi, chi, psi, omega. I don't know exactly what that is. That might be a, I think that's just an image here. But now this is for 1,000, they're going to this weird kind of stacked representation. Let's say let's go up to 2,000 here. They're kind of having a hard time, I think, you know, I guess that's the symbol for 1,000, is that A stacked up like this, but it's getting funkier as they try and go higher. One feature of our positional number system is you can represent as big a number as you want. So I can just type in a huge number here, and this number we can say it's, you know, 6 ones, 5 tens, 4 hundreds, 3 thousands, et cetera, et cetera, et cetera. We can get as big a number as we want this way. And of course, if we want to say, you know, that number, we can give it a name in English, and we typically have this convention that we call out every 1,000. So it's, you know, 1,000, there's millions, billions, trillions, quadrillions, quintillions, and at each stage here, we're kind of blocking this, just as you can see as this number is displayed, it's got little spaces between every block of 3 numbers, and each block of 3 numbers we're then sort of calling out with a name. That's the thousands block, that's the millions block, the billions block, etc. And we don't, usually we just use these names as a way to talk about these numbers. We don't try and do computation with numbers that have been written out with their names like this. But in a sense, we're doing something pretty similar to what folks did in the past, but we've got this nice clean notation that doesn't have any of these words lying around in it. So kind of the if we're the thing that so okay, so we've got this idea of numbers, and the idea of numbers, counting numbers, you know, 1, 2, 3, 4, 5, that idea certainly existed in the earliest recorded history we have. The idea of 0 as a number and the idea of negative numbers came much later. I mean, the idea of 0 as a number maybe was 2,000 years ago, maybe. The idea of negative numbers is pretty much 1,500. And came actually at the same time as imaginary and complex numbers came. Maybe we'll talk about those in a little bit. But let's you know, why did nobody need a representation for 0? Well, what is 0? 0 is nothing. Why would we need a representation for 0? You only start needing a representation for 0 when you start doing operations with numbers, and you try and do that in a systematic way. So let's talk about operations with numbers. So the first thing we think about doing operations with numbers is just look at the successive numbers. Just say the successor operation, which is basically a thing that adds 1 to a number. It's interesting that in Wolfram language, for example, we don't end up having a separate function, you know, successor that just adds 1 to something. But let's just, for our purposes here, just because it's going to be useful, I think, let's just invent a successor function. I'll just write it here. It's an extremely simple function, just adds 1. And so we can say, what's the successor of 10? And we'll get 11, and so on. Now, you know, an interesting question is, if we've got this successor operation, what happens if we just keep doing it? So we have this very convenient function nest. Actually, we'll have nest list, which will go ahead and progressively do something. So for example, let's just do nest fx3, for example. It will say, I'm going to do f, and then I'm going to do f on that, on the result of that, f on the result of that. I'm going to do that 3 times. So what do we get? If we take the successor of 0, and we take the successor of 0 3 times, rather unsurprisingly, we get the number 3. Let's say, however, that we took the successor of 6 3 times. What are we getting? Well, we're getting 6 plus 1 plus 1 plus 1. In other words, we're getting 6 plus, we can think of that as getting 6 plus 3. So in a sense, getting, when we add 3, it's like 3 times do the successor operation. So in a sense, we can think about addition as being successive successoring, so to speak. If we want to add 3, we do successor 3 times on the thing we already got, and then that adds 3 to what we have. So that's a so this operation, by the way, the notation of a plus sign to represent addition, that didn't come in until the 1400s. People were just describing things in words up until that time. And then the idea of, well, let's systematically represent this addition operation with a symbol that was separate from our numbers. So, okay, so the question then would be, this idea of taking an operation like the successor operation and just applying it many times, what happens if we take the addition operation, for example, and apply that many times? So what we have there, we'll say every time we want to say x goes to x plus 2, for example, and let's start with 0, and let's do this 7 times. And so what happens? Well, and I could have written, by the way, for the successor, well, let's just do it this way. We're saying we're going to be adding 2, so we could have written this, x plus 2. If we really wanted to be pedantic, we could write the x plus 2 as a nest of a successor of let's see, what am I doing here? I could say, oh yeah, of x 2 times. So that's our way of representing. This thing here means add 2. We could write out the successor there. If we really wanted to, we could write that out as in terms of another thing where we say this goes to thing plus 1, and that will be, so that's saying we want to take the result of successoring 2 times, we could say 5 times here if we want to, the result of successoring 5 times on our original number, and then we want to take that successoring, and we wanted to take that result of doing that successoring, which is addition, and we want to do that 7 times. So what is this? What is this iteration of addition? Well, the iteration of addition is multiplication. So in this particular case, we'd be saying 2. Let's say I had done the example here with 3, for instance. This is saying do the addition 3 times. And doing the addition 3 times is equivalent to multiplying by 3. So, okay, so let's see, what happens if we keep going here? Let's say so we've got this multiplication by, so let's say we have multiplication by 2, and let's say we've got the multiplication by 2, and we start off, well, I'm going to start here with a 1, and we're saying let's successively multiply by 2 every time. Okay, so if we multiply by 2 every time 3 times, what do we get? We get what we can represent as 2 to the power 3. Just like this operation of doing successoring, of doing addition 3 times, we represent like that. Or the operation of doing just the pure successor 3 times, we represent like this. So the plus is kind of we don't have a standard notation for the just do successor, but we have a standard notation that says, do the successor operation 3 times, do the nested successor operation 3 times, that's a times, do the nested times 3 times, that's a power. So obviously, given this, we might say, well, what happens if we go on with this? We could say, instead of this, we could say, how do we keep going? We could say we've got 2 to the power 3, and we could say, well, we could do this in a couple of different ways here. We could say, let's just do the squares each time. That's not very interesting. What we could do here is to say we've got, just like we've got a we could say we make 2 to the 3 by saying 2 times 2 times 2. We could say the next level up, we'd say 2 to the 2 to the 2. And that's 16. And if we go 2 to the 2 to the 2 to the 2, it's going to be that. And if we go 2 to the 2 to the 2 to the 2 to the 2, how big is that going to be? Oh, wow. That's a very big number. So this operation of successively taking powers, it's usually called tetration or power towers, and numbers get very big very quickly. So for example, we could represent this if we wanted to. We don't have a notation for this that's built in to Wolfram language because it's not an operation that one does very often, but we could say, for example, 2 up arrow 5 to represent this thing of taking 2 to the 2 to the 2 5 times. And that number gets very big. So for example, this number, I'm sure that number is way bigger than the number of particles in our universe. So yeah, it's 10 to the power 19,000. So that's the 10 to the 80th protons in our universe. So it's vastly bigger than that. So we get to a very big number very quickly. By the way, one of the things that's kind of a feature of what's going on here is you might say, how do you interpret that thing that's written down there? 2 to the 2 to the 2 to the 2 to the 2. What is that? Because it matters whether if we take 2 to the 2 to the 2, we get, well, actually, this, let me do one more level because otherwise we're not going to see this happen. 2 to the 2 to the 2 like that, we get 256. If we take 2 to the 2 to the, whoops, to the 2 to the, how many 2's do I need? 2, whoops, to the 2 to the 2, we're going to get that giant answer there. Did I have the wrong number of 2's? I had the wrong number of 2's there. Let me get rid of one of the 2's. Okay, we get a different answer. So it matters how we put the parentheses in here. It matters whether we're assuming that wedge groups to the left or groups to the right. Do the same thing with plus or something. We say 2 plus 3 plus 4 plus 5 plus 6. Okay, we get that result. We can put parentheses in anywhere we want. It doesn't make any difference. And that's a feature of the plus operation. We talk about it. It's this property of associativity that's true for plus and isn't true for power. For multiplication, same thing. We can do 2 times 3 times 5 times 6, and it doesn't matter. That's the same as 2 times 3 times 4 times 5 times 6. So one question is, when we invent a notation like plus, we might, or when we invent a notation like wedge for power, we potentially have to make a decision. What does it actually mean? In the case of plus, we got away with not having to make that decision of does it group to the left or to the right. For wedge, we do have to make that decision. So when we were designing Wolfram language, we made the decision wedge is going to group to the right, which means that that if we just type 2 to the 2 to the 2 like this, it's going to assume that we group those things to the right, and it's going to compute this rather than computing this. These things are pretty tricky. For example, let me show you another example. If I say, let's see, 2 over 3 over 4 over 5, what does that mean? Because it matters which way we group that. If we said 2 over 3, let me just put in some arbitrary grouping here, 2 over 3 over 4 over 5, we'll get a different answer. So it matters what 2 over 3 over 4 over 5, how that's grouped. And in that particular case, we choose to group to the left. So if we say 2, let's see, 2, I have to get the parentheses right, 2 over 3 over 4, oops, and that whole thing over 5, and that will give us 1 over 30. If we were instead to make the convention that we group to the right, we get a different answer. Let's type it in and see what we get. Let's see, put in a parenthesis there, put in a parenthesis there. Okay, that's now grouped to the right. Okay, we get a completely different answer. So again, it's a convention to see how we group these operations. And actually, people hadn't codified this very well. I mean, before I was building Mathematica and things like this, the question of what does this really mean was something where you ask people, reasonable people could disagree about what that meant. I'll give you another one, that's same type of thing. 2 minus 3 minus 4 minus 5. Which way does that group? Kind of exercise here. Well, if we were to say this groups, it groups to the left. It's assumed to group to the left. But if we had it grouped to the right instead, it would give a different answer. So again, it's sort of a convention about how things work. So another big convention, people learn in school is if you type something like 2 plus 3, let's type a nice times sign, times 5, what does that mean? Well, it could mean, let's see how we would group that. It could mean, well, let's just group it to the left, 2 plus 3 times 5. Or it could mean 2 plus 3 times 5. And it is an utterly arbitrary convention that got made in the, I guess in the 1600s, that if I type 2 plus 3 times 5, I mean do the times operation first and then do the plus operation, even though I wrote it out in this order where the plus seems to come first. So when people learn all these mnemonics, which I don't now remember, I'm sorry to say, for what operation do you do first, one has to remember one is basically learning a piece of frozen history. There's nothing fundamental about the fact that you do the operations in a particular order given this notation. It's just a kind of convention about what that notation means and how to interpret it. And so, for example, if we did this and we put in a wedge, the convention is, let's put in a wedge there, the convention is that means that the wedge binds tighter, it has higher precedence in the language of computer languages and formal grammars. It has higher precedence than times, which in turn has higher precedence than plus. So this expression groups like this. And that's a convention that it does that. And by the way, when we put in parentheses, we're kind of forcing a particular grouping. We're saying, okay, like in this case here, for example, we're saying, okay, the default is to say 3 times 5 is computed first, and then we add the 2. But actually, we want to do it the other way around. We want to do the 2 plus 3 first, and then we want to multiply by 5. Now, in fact, if you go sort of computeristic on this whole thing, we have to stop it actually evaluating these things. But then we can say something like this. We can say, show us the expression tree of this. And what we'll see is that the thing is, it's made this tree where plus is at the top, says do the plus, we do the power at the bottom, and it's the times of the power, the plus of the times of the power. We can also see that if we just look at the full form of this expression, we'll see that it's written out as power inside. If we were to do this without parentheses, let's see what, well, this particular one, I got it, I put in the parentheses in the right way. But if we were to do something like this, we would see in the full form of that, we have to hold it because otherwise if I don't use hold, it'll just evaluate it. This is 2, the plus of the 2, and then the times of the 3 and 5. And if we show the tree version of that, we can see it is a tree where the plus is on the outside and then there's times on the inside. If we did this the other way around, we'd see the thing work differently. So let's say it would be something like 3 times 5 plus 2. Again, we'd see that would be a plus on the outside of a times and so on, and the same thing with the tree. Okay, so that's kind of how okay, somebody is pointing out, okay, I don't think in British English math education that it was the same mnemonic, but apparently it's PEMDAS. What does that stand for? Parentheses, multiplication, division, addition, subtraction. Really? I wonder if it's that way around. In any case, the thing I'm sort of trying to explain is it's a convention that it works this way, and some extensions of that convention, like what you do with iterated division or what you do with powers, those conventions had to be made very, very recently. You know, these other conventions like times comes before, gets done before plus, those come from the 1600s. But, you know, I guess I got to make the convention for wedges and things in much more recent times. So, okay, well, let's talk about, we talked a little bit about things like, you know, we've now got notation for addition, et cetera, et cetera, et cetera. Let's talk about algebra for a second. So one of the things we might say is we could say something like, okay, we could test, is 5 equal to 4 plus 1? And it says, yeah, 5 is equal to 4 plus 1. We could work out what's 4 plus 1, and it's 5. And so we could say, you know, let's test, is 4 plus 1 equal to 5? Great, it's equal to 5. Okay, next question. If we know we've got 4 plus something, and that's equal to 5, how do we represent that? How do we represent asking the question, what plus 4, 4 plus what is equal to 5? And so people had this good idea in the 1400s that that one could start using letters to represent these kind of unknowns in an expression like this. I have to say, I think one of the reasons it took a while for people to have this idea is that until the 1200s, people have been using Roman numerals. So in Roman numerals, this would be, you know, if I say Roman numeral, I wonder what it's going to do. If I say Roman numeral 4 plus Roman numeral, well, plus, yeah, Roman numeral 1 or something, I'll see something like this. And, you know, and then if I have plus Roman numeral 10, oops, I've got an X right there in my number system. And so the notion of using a letter to stand for a number would be not an obvious thing to do if you were using Roman numerals to represent your numbers. But as soon as Hindu-Arabic numerals came in, it started to make more sense to say, let's distinguish the thing that we don't know, the unknown, from the things that are just numbers. So then we could start imagining, well, we have something like this. This is a, you know, 4 plus x is equal to 5. Okay, what's x? The point is that now we can start talking about things where we don't have to say, we could start just having things like 4 plus x. We don't know what x is. Okay, we say 4 plus x is equal to 5. Let's say we want to solve that equation, 4 plus x equals 5, solve that for x. Okay, now we discover that, oh, x can be equal to 1. But the important thing is that we've got this kind of slot that we can put in here that represents an arbitrary thing and represents an unknown. And that was kind of a big idea of the 1400s. And the kinds of equations, the kinds of things where you could say this is equal to that, well, you know, we could start saying 5 plus 3x here. What value of x gives that? Oh, interesting. Well, there's a minus sign there. So that's going to be important in what we're about to talk about. I should have perhaps mentioned that the other type of numbers that comes from a long time ago, comes from antiquity, people like Pythagoras were very interested in them, were rational numbers, numbers that are the ratio of two other numbers. And so, for example, we can say, well, what do we get if we say, 6 divided by 2? Great, we get 3. What do we get if we say 6 divided by 7? Well, that's just a 6 divided by 7. We don't know what that number is. Now, much later in the 1600s, people had the idea of decimal numbers, the idea of extending this notion of positional notation to fractional numbers. So that's, the 1/10, 100th, etc. That was a very late idea. That idea emerged only after the invention of things like logarithms and so on. Before that time, people were representing numbers just by giving them in the form of fractions like this. And so, for example, the Egyptians, famously, they didn't know about numbers like 2/3. That wasn't a thing for them. The only kinds of numbers they talked about were numbers that were 1 over something. So I think, let's see if we've got one of these. I think we probably have a thing. Let's see. Here we go. So if we take 2/3 and we write that as an Egyptian fraction, the Egyptians always were writing numbers as 1 over something plus 1 over something. So 2/3 better be equal to 1/2 plus 1/6. And it is. But to the Egyptians, our current notation of 2 divided by 3 represents 2/3. They didn't have that. They were just saying, let's write out everything as 1 over something plus 1 over something. So let's try a different fraction here. Let's try something like, I don't know, 7/8, let's say. Okay, 7/8 is apparently 1/2 plus 1/3 plus 1/24. Let's work that out. See if that's right. Yes, it is. And let's maybe try let's try something else. Let's try a number like, let's try something really kind of huge like this. Okay, in this Egyptian way of doing things, you got a pretty big number there to represent this. So, but this was this is clearly a way to represent rational numbers. It isn't the way we use, but it's a way that you could use. The Egyptians used it. The Babylonians had a different way of doing this. I don't know whether we can do that here. With more like our notation, with powers of 60 and inverse powers of 60. All right. Well, let's see. We're going on talking about different kinds of numbers. The next kind of thing that happens is we got these equations. Okay, and we've got equations, and they're things like 4 plus x equals 5, solve for x. Okay, given that we're doing that, what about other operations? What about, 2 times x plus 6 equals 7? Okay, we can say solve that for x. And okay, the answer is x equals 1/2. One feature of equations like this, equations where we're just multiplying and adding and so on, we could write out all kinds of fancy equations where we're multiplying and adding things and so on. And one feature of those equations is anytime we do that, and we put x's in there, anytime we do that, the value of x we get out is always a rational number. It's always a ratio of 2 whole numbers. And so that's a thing. But now let's start multiplying more x's in here. So let's say we say x times x equals 4, let's say. Okay, so if x times x equals 4, what's x equal to? And the answer that Pythagoras would have known is x equals 2. The idea of x equals -2, as I said, that comes from 1500. That's a much later idea. But so for right now, let's just concentrate on x equals 2 here. So we're now saying we can solve this equation, x times x, or x squared equals 4, and the solution for that is x equals 2. Okay, so then, but Pythagoras thought that every equation you could write down, you could solve using rational numbers. And so then he wrote down the equation x times x equals 2. And he was very confused because he couldn't find a rational number. There's no, forget the Egyptians with the big numbers in the denominator. There isn't, he couldn't find a rational number that could be multiplied by itself to give 2. Even if he had something, let's say we've got, let's try and approximate it. Let's say I'm gonna use a tricky fancy thing because I know how to do it. Let's try and do this. Let me see. Let me try this. I'm just going to do something fancy just to show this. Okay, let me do this. Oh, no, actually, there's another way to do this. Ooh, there's a better way to do it. No, actually, I'm going to do the thing I was just about to do. All right, let's do this. And actually, I might talk about continued fractions, which were another way of representing numbers that became popular later on. Okay, so here we've got a sequence of rational numbers, and let's compare those to the square root of 2. So let's take those things, let's take the numerical value of those things, and let's look at the numerical value of the square root of 2. Okay, so what we see is these rational numbers are getting really close to the square root of 2. And Pythagoras, who knows whether he worked any of these out, maybe he got as far as 41/29, I don't know. And he was like, well, that might be almost square root of 2, but wait a minute, it's not exactly the square root of 2. And in fact, what he eventually found was a proof that the square root of 2 can't be a rational number. And that was a big and confusing thing at the time. So what is the square? If the square root of 2 can't be represented as a ratio of two numbers, what is it? And that was a thing that was kind of left hanging for a very long time. It's what we would these days call an algebraic number, but it's a number that is, in a sense, you can just say, well, the square root of 2 is the solution for x in the equation x squared equals 2. That's the definition of the square root of 2. And maybe there's nothing more that we could say about that. Well, okay, so let's ask the question, let's take equations of the form, let's say, x squared plus 5x plus 1 equals 0, for example, or solve that for x. Okay, that's the famous quadratic equation. That's the equation where everybody learns the formula for if we put in a, b, c here, everybody learns this formula, that the solution to this equation is given by this formula here. This was discovered by the Egyptians for sure, and was something where now notice with this formula we can see something, which is every quadratic equation, every equation of the form something times x squared plus something times x plus a number equals 0. Every quadratic equation can be solved in terms of the square root of a number. So if these numbers here, a, b, and c, are integers, we are guaranteeing that every quadratic equation, whatever integers we feed in here, the solution to that quadratic equation will always be a formula that just involves square roots. So that's kind of an interesting result, that you can solve any equation. You know, we know that x squared, if we just have x squared equals 2, then the solution for that is x's square root of 2. But this is telling us that the bigger equations, the equations that involve other linear terms and so on, they can all be solved in terms of square roots. Okay, so then we get to the 1500 roughly, and a chap called Cardano, another person called Tartaglia, Ferrari, a whole cast of Italian characters. And they got interested in solving cubic equations. So that's equations of the form x cubed, so x times x times x. It's called x cubed because the reason it's called x squared, right, is that if you have a square and its sides are both of length 2, then the area of the square is 2 times 2. So that's why one talks about 2 squared being 2 times 2 and so on. 2 cubed would be, you've got a cube whose sides are all of length 2, so the volume of the cube is 2 times 2 times 2, or 2 cubed. Okay, so then Cardano. So Cardano got interested in solving cubic equations. Well, cubic equations are a giant mess. Let's see. I think we might be able to say this. There we go. Okay, this is the solution to that cubic equation. So it has all kinds of messy things in it. It has a variety of roots. Let's take a look. One of these will probably be a, oh boy. Okay, we're trying to solve this cubic equation. It's a total mess. we have, you might have thought, oh, it's just going to involve cube roots. Well, it does just have cube roots in here. But the thing that Cardano noticed is that essentially, as soon as you start talking about solving cubic equations, you can't get away from having negative numbers. And when we talk about, oh, we've got 5, take away 6. Okay, people had invented, for example, if you're doing accounting and you say, I've got $5, guilders, whatever, I've got 5, I've got to pay you 6. How many do I have left when I've done that? Well, accounting, if you're doing accounting and you're trying to, keep records of what you're spending and so on, you might end up wanting to say, well, I'm making my account book and I want to represent the fact that I owe you $1 or something at the end. I don't have, at the beginning, it's just like, well, I start off with my $5, I pay somebody $1, I get left with $4, et cetera, et cetera, et cetera. I've just got some number of dollars. What does it mean if I've spent more dollars than I have? How do we represent that? Well, people like Luca Pacioli, who was a friend of Leonardo da Vinci's and was sort of the originator of things like double entry bookkeeping and the kind of notion of making sort of general ledgers for accounting, this idea of what do you put on your accounting ledger if you actually owe $1 and it's not like you have $1. And even in modern accounting, actually, I think we have gosh, I haven't used this in millions of years, but in Wolfram language, we have an accounting form which shows the representation that's usually used in accounting data for a negative number. So if we were to make a table of numbers from n from minus, well, let's just say the accounting form of that, n from minus n from -5 to 5, okay, that's the way one would typically write out a negative number. Perhaps not so much very recently, but that's the typical convention in accounting. I don't know whether Luca Pacioli used that convention. Wouldn't be surprised if he did. I mean, the notion, maybe he used red ink, hence the term in English about that in accounting. But anyway, this is a possible notation for a negative number. The subsequent notation that I think Cardano already used was to have a negative sign. Okay, so big achievement of Cardano, big argument over who invented this. He figured out how to solve cubic equations. In fact, he figured out a general formula that lets you, for any cubic, I could just fill in ax cubed plus bx squared plus cx plus d equals 0. And the result is a total mess. But this is what Cardano figured out. And big achievement. But one of the things that happened here was he realized you really have to, as soon as you're sort of enumerating roots of a cubic equation, you really have to start talking about negative numbers. But actually, he ran into another thing as well. If you look carefully at this formula, you will see a little I here, okay? As many of you will know, that's the square root of -1. Okay, so here's what Cardano ran into. He said x times x equals 2, great. We can solve that, and we can say x, actually, let's do x times x equals 4. We can solve that, that's all good. It's, the results are either 2 times 2 is 4. Great, -2 times -2 is also equal to 4. But now the question is, what happens if x times x is equal to -4? What value of x? It's kind of the same thing that Pythagoras ran into. What rational number is it that gives me square root of 2, that gives me a 2 when I multiply it by itself? What number is it that gives me -4 when I multiply it by itself? Okay, and so then what happened is that the idea got invented of imaginary numbers which just have this thing I, and the idea is that 2 times I is just this thing that we invent, which has this property that I times I is equal to -1. And so we can start saying, 5 plus 7i, and we can look at that number and we can say, what's that number squared? And we can do all sorts of arithmetic, all sorts of standard arithmetic that we can do on ordinary numbers. We can also do on complex numbers or imaginary numbers. Imaginary numbers are just the things like 7i, for example. Complex numbers means the real part plus the imaginary part. Okay, so if we look back at our cubic equation here, and we look at this cubic equation here, well, we got this big messy solution here. If we look at what that actually is, what we'll discover is that big messy solution. If we say what's the numerical value of that, it'll be minus that number, that real number, and then here it's got two complex numbers involved. But there was this formula, and one of the things that happens is that even when, so look back at the big formula here. The big formula here involves I. And even when the actual answers are all real numbers, it's still the case that the formula in the intermediate stage of getting those numbers, you end up dealing with complex numbers. That's something that's still not terribly well understood. In the end, you've got a cubic equation, it's got real numbers in it, it's got integers in it. Then you've got this formula for working out the solution, and in the formula, you're doing things with complex numbers, and then when you work the formula out, at the end, you get ordinary real numbers without any imaginary parts, sometimes. Often, most cubic equations don't have real roots. Most cubic equations have complex number roots. They usually have a real root, two complex roots, and so on. So, okay, so just for fun, we can look at what happens with equations of the fourth degree, which were actually solved around the same time as equations of the third degree. That is, well, we have, let's see, let's fill this in, c squared plus d times x plus e equals 0. And let's take a look at that equation, what the solution to that equation is. Okay, it's a monumental mess. Let's make my screen bigger just to enclose it. These are the different solutions. So remember, we went from the quadratic formula, which we can sort of more or less remember. I don't think anybody was, except for maybe the guys who were originally arguing about who invented it, memorized the formula for the solution to the quartic equation, to the equation of the fourth degree. But notice if we go and dig in here, if we look in great detail, we will see somewhere here, we'll see 2 to the power 1/3, that means the cube root of 2, that means the solution of 2 times 2 times 2 of x times x times x equals 2. I think if we dig carefully here, we will see, do we see fourth roots here? I don't think we do in this representation. There are other representations where you do see fourth roots. But the thing that's worth realizing is, if we were to ask kind of, how can we solve this equation? In principle, we've got this formula here that involves square roots and cube roots and fourth roots. It's just taking roots of numbers, and that eventually allows us to solve the equation. Okay, so that was 1500. Then a question that exercised people for 300 years was, well, what about equations of the fifth degree? What about quintic equations, where we have an x to the 5 in here? Can we go and do the same thing again? Is there a solution to the quintic that involves just square roots and cube roots and fourth roots and fifth roots? That was a big question for a long time. So in the 1830s, Galois proved that it wasn't possible, proved that there is no formula for the solution to the quintic equation in terms of just roots, that there's no way of writing a pure formula like that. It was actually an important result because it was kind of an impossibility theorem, a little bit like the Pythagorean result, that there's no way to find a square root of 2 represented as a rational number. The Cardano result, there's no way to solve the cubic without involving complex numbers. And then the Galois result, there's no way to represent the solution of an equation of the fifth degree without going beyond square roots and cube roots and so on. And normally people just say you can't solve the quintic. That's not really right. I mean, if I type in, your average, I'll type in some random quintic, and well, some quintics, if I just type a quintic at random, my chance of hitting a quintic that's easy to solve is rather low. But okay, what we do in Wolfram language here is we represent the solution to the quintic as these approximate numbers. But if I were to say, for example, let's say I just say, give me the possible values here, and I were to say, let's just add all those up. I want to do this. I want to say, what is all of that? Okay, it's -6. Wow, that's interesting. Notice that 6 is the coefficient of this. Turns out to be a general fact that the sum of the roots is that, depends on that coefficient there. So there are things we can do with these numbers, even though these numbers we could represent approximately, but we can't like pick it up and say, oh, it's the fourth root of whatever. Even though we can't like pick it up and say there's a formula for it, we can say, I've got this number. Here it is. I've got an implicit representation of it. That number is a root of this equation. It is the third root of this equation, for example. I can pick it up and do things with it. Like I could take that number. If I take that number, I can perfectly well say, what's that number to the fourth power plus 5? Okay? And I can treat that number just like I could say there's an x there. I could treat that number like this. I can then say, let me work out what the numerical value of that is. But I'm just treating this as an arbitrary number that's just sort of hanging out there. So in any case, one of the things people say is you can't solve quintic equations. You can solve them implicitly, where you have these kind of algebraic numbers. This is something we figured out for mathematical and Wolfram language many years ago, is kind of the implicit representation of root objects, as we call them. Actually, there's also another solution you can give in terms of elliptic functions, which are a kind of a fancy kind of generalization of sines and cosines. Maybe we'll talk about those maybe in a bit. But the idea is there is a formula for the solution to the quintic, but it doesn't just involve square roots and cube roots and so on. It involves exotic other functions. By the way, I should say there's a formula for the solution to the cubic that involves sines and cosines, trigonometric functions. You can, instead of using square roots and cube roots and things, you can write it out in terms of trigonometric functions, and those sort of unravel, just like the complex numbers eventually unravel to give you other things, so the trigonometric functions unravel to give you other things. The analog of that for the quintic is the elliptic functions, which don't necessarily unravel. For a quintic equation, or actually an equation of any degree, there are representations of the solution either implicitly or in terms of these higher order elliptic functions, hyperelliptic functions, and so on. So in any case, that's but let's come back to what we were talking about, complex numbers, the thing of the 1500s. That was and we can do all sorts of things with complex numbers. I mean, we can complex numbers have a lot of the same properties as ordinary numbers. So for example, what are some properties? Well, actually, now that we're talking about algebra, we can talk about some other things. So for example, if I say y plus x, that we don't know what x and y are, but whatever they are, we know that y plus x is equal to x plus y. And that's a general property of plus that we can sort of algebraically describe independent of what these values actually are. We can fill any values in here, but just as a matter of algebra, these two things are equal. So we can do all kinds of stuff with algebra now. So we can say x squared minus 1. Okay, great. That's equal to minus 1 plus x squared. But now it's also the case that this is algebraically equal to x plus 1 times x minus 1. So if we say something like, is x squared minus 1 equal to 1 plus x minus 1 plus x, actually Wolfram language will at first just say, I don't know. If we substitute a particular value for x, like we say x equals 6, it'll definitely be true because there'll just be two numbers and they're equal. But we can also take this and we can just say, simplify that. Tell us a simpler form for this. Okay, it's true. Great. And in general, once we have algebra, okay, when we have a number like 56, there's just one way to write out that number. even writing out a fraction like 2/3. We already saw that the Egyptians had a different way of writing out 2/3. We could write out 2/3 as, or we could write out 7/8 as the sum of these Egyptian fractions, or we could write out 7/8 as our 7 divided by 8. We could write it as instead here as just this plus this plus this plus this. So again, it's not self-evident what the fact that we choose to write numbers as we choose to write 7/8 as 7/8 rather than 1/2 plus 1/3 plus 1/24 is, again, one of these sort of conventions about what we do. By the way, I might mention that one of the things that's always interesting with fractions is, if we say something like 4/6, right? We could write 4/6 as 4/6, but we choose to reduce that fraction to lowest terms by dividing through by 2. And in fact, it becomes a question, which fractions can we do that with? Like if we say table of I over j, well, let's say I over 7, I goes from 1 to 7. Okay, so some of those, like once, oh, I'm sorry, I shouldn't have done 7, silly me, 10. Some of those, the only way we can write them is 3/10, but this is 2/10, and we can alternatively write it 1/5. And so this is, so there's, you could ask a question like, for how many numbers, how many of the I over 10, whatever we call this, n over 10, for how many of the n over 10 fractions can we reduce them, and how many of them get stuck as n over 10? So we can go ahead, let's do this for 100, for example. Let's see, we can just count. Okay, we've got more of these numbers here. And for example, let's say, I'll tell you what, let's just do this. Let's say we want the numerator of that, so that will have reduced it to lowest terms. We get the numerator, and then we ask, how many times do we get a numerator equal to 1 here? Okay, so let's go ahead and do this for different numbers n, and let's make a table for every number n of how many fractions of its fractions, how many of them. Okay, so this is the result. So for which of its fractions get left as 1 over something? Okay, so here we're going, oh, whoops, you know what I should have done? I should have said n-1 here, because we don't really want to divide a thing by itself. So this is saying 1/2. Okay, this is one of those. In the case of what am I doing here? This one here is, which one am I getting? What am I getting here? That should be what am I getting? Table of the numerators. Yeah, I think I did this right. Oh, I see. That's 1/2. I'm confused here because I should have 1/3. Oh, no. I'm sorry. I did this wrong. Very silly. What I should have done, I got myself totally confused here. What I should have done was, let's say I make the table of m over 10. M goes up to 10-1, 9. Okay, so the real question is, which of these numbers still has a numerator of 10? I was going Egyptian on us and looking at which numbers have a 1 in the numerator. That's not what I wanted to do at all. What I want to do instead was I asked which numbers don't reduce, which numbers just stay with a 10, which numbers are not reducible to lower terms. So that would be the denominator here of that equals n. Okay, so this is, am I going crazy here? Let's just look. Denominator of that line 143. Okay, great. Denominator of I over n. Okay, what am I doing wrong here? Let's see. So let's say this is for 10. I over 10 equals 10. And let's go, well, let's just do these. Denominator of I over 10, I goes up to 9. Oh, silly me, silly me. I want to count, yeah, what I'm doing here wrong is I'm counting the number of ones. I need to count the number of times that it's true that that's equal to 1. Okay, so there we go. So this is now the number of fractions that don't reduce to lowest terms. So there's 1/2, there's 1/3 and 2/3, there's 1/4 and 3/4 there. We could just give, if we wanted to, instead of just counting the trues, we could just select, we could just say, for which of these is it true? So we could select in, well, it doesn't really matter. We can give the list of what numerators. But anyway, this is the number of, there's a number of fractions with denominator n that just stay with denominator n. They're not reducible. Okay, and so if we plot this, let's see. Well, we can just say let's line plot. It's a pretty wild creature. Looks like that. And so this is a complicated thing. It actually has a name. It's called the Euler-Phi function, sometimes called the totient function. And if we work out the Euler-Phi function of n, for n goes up to 50 or whatever, we should see the same numbers there. It has a different convention for 1 here, but we see the same numbers showing up here. And you know, one thing, if you really start looking carefully, you'll see that for prime numbers, this thing is equal to just the number -1, and those are the maxima. Here are the prime numbers, so that's 43. There's another maximum at 47, another maximum at 41, and so on. We can talk about, well, okay, let's talk about prime numbers for a second. So prime numbers, again, known in antiquity, known to Pythagoras. What is a prime number? Well, if we say, if we have the number 20, for example, we can write that number as 2 times 2 times 5, I hope, if I know my arithmetic. And yes, 20 is 2 times 2 times 5. And many numbers have the property that you can factor them. You can write them out as factors like this. And we can even say, if we say factor integer, we could even make a table here of a bunch of numbers and their factors. And we could say n goes up to 20. And we could make a nice grid here that, let's just make a nice looking grid. And this will now be, on the right, we're showing kind of representation of the factors of the number. So this is showing that 6, this is 2 to the power 1 times 3 to the power 1. Or 13 is just 13 to the power 1. 14 is 2 to the power 1 times 7 to the power 1. And the way we can think about this is which numbers don't have this property that we can write them out as a multiplication of other numbers. So, you know, we can do it in a kind of a cheating way. 13 is 13 times 1, but let's say that doesn't count. And let's imagine that we are trying to make, let's say we're trying to take, let's say 14 squares, and we're trying to make a rectangle out of 14 squares. Well, we can do that. We can say it's a 2 by 7 rectangle because 2 times 7 is 14. And so we can arrange squares in a rectangle to get, or we can arrange dots in a rectangle, and we can have 14 of those in that rectangle. But there are some numbers where we can't arrange them. There are numbers, you know, we often talk about a number like 16 is a square number because it can be, you know, if we make, I don't know, let's just make a table of, let's do this. We can make a, we really do it pedantically here, we can make a table of 16 little dots, and we can partition them, and then we can make a grid of those, and we can plainly see that our 16 can be arranged in a square. If we say, well, how about 14? Can we arrange that in a square? And the answer is, well, yes, if we have 14, then we can arrange it in a square, which is 2 times 7. And if we have 20, we can arrange it in a square, actually, sorry, in a rectangle. If we have 20, Well, we can arrange it in a rectangle in different ways. We can arrange it in a rectangle like that. We could arrange it in a rectangle like this, and so on. But the question is, can we arrange it in a non-trivial rectangle? The question here is, and that's the numbers that we can't arrange in rectangles. Those are the prime numbers, the numbers that we can make up as units, that we can use as units to build other numbers out of. And it's a fundamental theorem, often called the fundamental theorem of arithmetic, that every number, every ordinary number, has a unique factorization. There is, if we try and represent that number in terms of primes, there's a unique way that that number can be represented in primes. It's 2 to the power 3 times 7 to the power 1, where 2 is a prime and 7 is a prime. There's always a unique way to do that. And that's a fundamental fact about integers. It doesn't happen to be true for other kinds of numbers, but it is true for integers, that you can find these discrete set of primes that, for which where every integer can be written as a product of those primes. Now, to tell whether a number is prime, one very simple way to do that is to just say, well, can you divide it by anything smaller than it? If you can't, if you have the number 56, you might say, well, can it be divided by 2? Yup, it can be divided by 2. So it isn't prime. And so then we're and one way we could test is something prime. We could just say, try dividing it by a whole series of numbers. Let's try just dividing it by first 10 numbers. Okay, there are cases where it divides exactly, where it doesn't get left as a fraction. So this number isn't a prime. Let's try 57. Okay, 57, I didn't actually know if 57 was a prime immediately. 57 isn't a prime because look, it's divisible by 3 there. Let's try 59. Okay, looks like 59 is a prime. How far do we have to go in doing these divisions? Well, we definitely don't have to go further than 8, because by the time we've got 8 times 8, we've got 64. So if 59 isn't divisible by 8, there's nothing. If it was going to be divisible by anything, it's got to be divisible by something less than 8, because by the time we've got to 8 times 8, we've got a number bigger than 59. So this is this is kind of the so that's how you work out whether a number is prime. Actually, there are vastly more efficient ways to work out whether a number is prime. There are all sorts of cool tricks. There's this thing called Fermat's little theorem, which is not his last theorem, but his little theorem, which actually relates to this Euler phi function that I was talking about before. And there's this property: you fill a number into a particular formula, and if it's prime, that formula has to work out in a certain way. And so that's a sort of a cheap way to test to get a good estimate of whether a number is prime. If you try that test a bunch of different times, you can get a higher and higher probability the number is prime, and then people figured out how to get a deterministic version of things like that. But anyway, you can work out by something much more efficient than just doing successive divisions whether a number is prime. And there are all sorts of things to say about the distribution of prime numbers. And it's been a big driver for mathematics to work out what the distribution of prime numbers is. When we make a big table of prime numbers, we can make a table of the first, let's say we make a table of the first 1,000 primes, and then let's say we plot those first 1,000 primes. Endless work has been done on, oh, that looks very regular, doesn't it? Let's go down to 100 primes. It'll look a bit less regular. Endless work has been done on trying to figure out what you can actually say about that curve. And for example, roughly how fast does the curve go up, and all these kinds of things. So this is, so that's the story of prime numbers. Actually, in the time of Pythagoras, prime numbers and perfect numbers were really neck and neck as being equally important. Perfect numbers, so if we look at the divisors of a number. So divisors are all the numbers less than that number that can be that can divide that number. So trivially 1 and 10 divide 10, but also 2 and 5. So if we say divisors of 100, we'll get a whole bunch of numbers. And one of the things that Pythagoras really was interested in was numbers where if you add up all the divisors, so you take the total of the divisors, how does that compare to the number itself? And a perfect number, I think we actually have, yeah, we have a perfect number is a number which has the property that the sum of its divisors, except for itself, is equal to the number itself. So if we go here and we say, let's work out the divisors of six. The divisors of 6 are 1, 2, and 3, and the trivially 6. And the sum, so if we say, let's take the total of most of that list, and we get 6. Okay, so for what numbers is the sum of their divisors equal to the number itself? And so we could just go through and we could find the total of most of the divisors of m of n, and let's work that out for a table of that for n goes up to, let's say, 100. And these are, so these, this is, yeah, okay, actually what I should do is subtract the number itself here. Actually, let's take the number itself. No, we can subtract the number itself. Okay, so here, most of the time, we don't have, actually, this is a funky curve. I wonder what this even looks like. I don't even know what this looks like. I'm not sure okay, so this is a curve that says, what's the difference between the number and the sum of its divisors? And occasionally, it's 0. That is what Pythagoras called a perfect number, a number that's equal to the sum of its divisors. And if we look here, let's find which of these. Let's find the first few perfect numbers. Let's say what's the position in that list of the perfect numbers, of the zeros, and we'll find 6 and 28 are the first 2 perfect numbers. What's the next perfect number? Well, the next perfect number is, oh, why is that? Oh, I was typing in the wrong place. That's why I was not seeing it. Okay, the next perfect number is, so that was, the third perfect number is 496. Okay, the fourth perfect number is probably quite a lot bigger. Let's make a table of perfect numbers, and n, let's go, n goes up to, let's say, 10. So those are the first 10 perfect numbers. They get pretty big pretty quickly. And these perfect numbers are related to primes of the form 2 to the n minus 1. There's a whole story about that Pierre de Fermat was much involved in. That's a different story. But what we see is there are perfect numbers. So this number here has the property that the sum of its divisors, let's work it out. Let's prove that that's a perfect number. Let's work out its divisors. If I could spell. There are its divisors, and let's take the total of those. And okay, we have to subtract the number itself, and then we'll find out it's equal to the sum of its divisors. Okay, so one thing Pythagoras wondered is, look at these perfect numbers. He only knew, I think, the first 3 maybe. These perfect numbers are all even numbers. And it's probably the oldest unsolved problem in mathematics. Are there any odd perfect numbers? Are all the perfect numbers even? Clearly, the perfect numbers are few and far between, but the question is, could there ever be an odd perfect number? Nobody knows the answer to that. It's been an unsolved problem for 2,000 years. So it's kind of interesting to see how quickly one gets to that. But perfect numbers are about sort of making numbers up from their parts, from their additional parts under addition, usually called aliquot parts. And back in antiquity, people were no more interested in primes than they were in perfect numbers. Primes turned out to be much more fertile from the point of view of thinking about mathematics. Well, I should wrap up in a moment here, but I think what we were talking about here was the representation of numbers in terms of primes. And one question you can ask is, if we ask to factor, let's say I was talking about, we're talking about things like complex numbers. Let's see. How do I get a good one that isn't? Let's see. Come on. Oh, that's what I need to do. Factor integer. What was I doing? I was doing the wrong thing. Okay. Funky fact about complex numbers. They also turn out to have the property that, is that right? Yes, I think they're a unique factorization domain. Somebody, I think that's right. Yeah, anyway, this is a way to factor 8 plus 2i as minus I. These are essentially the Gauss, the primes. So we can ask something like, is 7 plus 5i, is that a prime with respect to, in terms of complex numbers? So we could say here, we can say factor integer, that thing, I think we default to, yeah, we do. So that shows that this is actually 7 plus 5i is actually I plus 1 times I plus 6, 1 plus 6i. So if we ask about 1 plus 6i and we say, is that a prime? I think it will default to, it will say, yes, that's a prime. If we say 1 plus 7i, for example, chances are that's not a prime. And again, we try and factor that. We'll see that that can be factored into complex numbers. So that's a feature of complex numbers. It's not a feature of other kinds of ways to construct numbers, that they have this way of having the notion of primes. But primes are kind of that's the big result is that every whole number, every integer can be uniquely factored into primes. It's not like a rational number where you can write it out as a sum of other rational numbers like the Egyptians did, or another way. There's a unique way of representing any integer as a product of primes. That's the often called the fundamental theorem of arithmetic. So, well, we were talking a little bit about algebra. I was wondering whether I would make it as far as calculus. If you guys have thought this was fun, I thought this was fun. Maybe I should go on another time and see if I can make the bridge from algebra to calculus and beyond. I think I'll be able to do that. I would predict it's another 45 minutes to get into seriously into calculus. But I think what I was showing you before was I was trying to show you that when we have different, when we have an expression like x to the fourth minus 1 or something, there are different ways to write x to the fourth minus 1. And that's a feature of we can represent the same algebraic expression in different ways. With integers, there's one obvious way to do it. With algebraic expressions, there are different ways to do it. A very common way to think about it is in terms of so-called polynomials, which are sums of the form x to the 1 plus x to the a number plus x to the 1 plus x to the 2 plus x to the 3 and so on. Kind of the analog of writing out a number as 1 plus something times 10 to the 1 plus something times 10 to the 2 and so on. You write out a polynomial in which you have, we could actually do this in a funky way here. We could say, we got a list of digits here, and we could say, put an x there. Oh, come on. We could write it out like this. This is kind of, instead of a 10 here, we're just putting an x there. This is kind of this is sort of the algebraic equivalent of a number written in positional notation. It's called a polynomial, and we get to do all kinds of things with polynomials. And there isn't just one way to write out this polynomial. We could write it out in different forms for any value of x. These forms will always be equal, but they have different structures. And that's kind of a big thing when you do algebra. You're typically transforming from one of these forms to another of these forms. And there's not really a best form. You might say this form as an expanded polynomial is the best form, but for other purposes, you might say this factored form is the best form. There are all sorts of best forms. All right. Well, okay. Sounds like people were having some fun here. So All right, I'll go on and I'll do this another time, and we'll make it to calculus and beyond, and see how far we can get with math. See how many uh, see how many weeks, months, years of math classes we can compress into a short amount of time. I would say that the key thing that's letting me explain all this stuff is that I'm just typing stuff into Wolfram language and we're seeing what happens. That's kind of why we're able to, I think, as easily as this, sort of explain what's going on. Anyway, well, that was fun for me. Thanks for joining me, and we'll find the time to schedule another of these live streams. And maybe I should upload this. Let me go ahead and do that. Actually, I am going to, let me share again for 1 second, and let me go ahead and upload this notebook that I just created to the cloud, so you all can play with it. So let's go ahead here, and it says upload to the cloud. I'll just publish it. I'll publish it on my account here, and I'll just say publish, and you should get that. And I can put this in, well, here. We can do very, very weird tech. If I was doing this in person, I might just show you that barcode. Oops, there we go. If you go to that on a phone, you should be able to open this notebook. And I will also put the, maybe somebody can add this to the chat session. I can, just to show you what this does, if I go there, I can go, oops, here we go. This is just a web browser. I opened up our math story in a web browser here. If you go there, and you can, if you have a Wolfram ID and an account, you can go and start just, actually, this is a public copy, so you can say make your own copy. You make your own copy, and you can start editing this. And I could change that. Oops, did I make my own copy? See the original, you are viewing a copy of the original file. Okay, so here I can just edit that to a 5 and recompute it. And once it's loaded in. And so you can do that too. You can create a Cloud Basic account if you don't already have one, and play around with it. And okay, so next time we try to get to calculus. So see you another time. Bye for now. Okay, well, actually, just a minute. I have a small technical problem here. I think we have to restart this. So let's,
We're on live.
okay, so Rocket
Could you
Chat
see
is
Rocket
broken.
Chat?
Yeah, it's broken. Stupid, stupid,
Ah.
stupid, stupid, stupid. Okay, hello everyone. Sorry about that technical glitch. Well, welcome to another math storytelling day. I realized I did this a year ago, and people wanted me to continue from where I'd left off. And I've kept on meaning to get around to doing that, and I hadn't before. The year's gone by, so now I'm going to go ahead and do that. So last time I talked about sort of very foundational questions about math. We talked about numbers. We talked about properties of numbers, primes, things like this. We got as far as talking about some algebra. And I said, gosh, if I went on, I could talk about things like calculus. And people said, yes, please talk about that. So here, finally, I'm back. I'm going to talk today about things like calculus. We'll see how it goes. I should, so I think the, let me go ahead and let me just remind people about what I talked about last time. You can find a link to that video and the notebook that I used, and I'm using my kind of medium for talking about things and thinking about things is always Wolfram language. This is kind of my way of both kind of having a concrete computational way to think about math and my way of actually getting a computer to help me do things and my way of showing people in kind of computational essay style what's going on. So last time we talked about the kind of the very origins of mathematics, from just pointing at different kinds of things to saying we can characterize the number of things by a number. We talked about how different civilizations at different times have represented numbers, whether it's the Babylonians, the Greeks, the Roman, and so on. We talked about how that worked. And then we went on and talked about kind of what you can do with numbers, from just adding numbers up to taking powers of numbers, to taking towers of powers of numbers. We got some very big numbers here. And we talked about some of the things about how you write arithmetic expressions. And then we started talking, if I remember correctly, yes, we started talking about the origins of algebra and when you can have a symbol like X that stands for any number. And you can say things like 4 plus X equals 5. And you can say, well, X stands for any number, but which number would make 4 plus X equals 5 true? They say, well, that's equal to 1. And that's how we're starting to do algebra. And we talked a bit about that and about equations like quadratics and cubics and so on, and all the complicated things that happen when you try and figure out what value of x makes x cubed, that's x times x times x, plus 5x plus 1 equal to 0. For what x is that true? And it turns out you can say, as an approximate number, you can say it fairly easily. As a sort of a formula, it's something quite complicated. So we talked a bit about that. And where did we get to? We talked about primes a bit. And we were going to then start talking about things like calculus. So let's go back and talk a bit about formulas. So when we have something that says something like, okay, let's see, do I need to make this even bigger? Perhaps I'll make it even a little bit bigger there. So we might say x plus x plus x. Well, for any number x, x plus x plus x is 3 times x. So we can do these algebraic transformations that say we write down things with x's in them, where x stands for any number, and then we can do so. If we say x minus x, for any value of x, x minus x is always 0. So we can simplify that to just 0. Now things get more complicated. For example, let's say we say x times x. Okay, we can write that as x squared. That's just a notation. The little 2 superscript just represents kind of how many times we multiply by x here. So we could say x times x times x, that many times you get x to the 5. If we said x times x times x times y times y times y, we'd get x cubed times y cubed. Maybe we could put another x in here somewhere. And we're basically just counting the number of x's and the number of y's that we're multiplying together here. But that's a notation for these things. But we can also directly say if x was equal to 2, for example, we'd say 2, and we can type that as wedge 5, or in Wolfram language, we can just say control wedge and then put a 5 right up there, and we can compute. So that number better be 2. I know that it is 2 times 2 times 2 times 2. It's 32. Okay, so the point is that something like x squared we can think of as a formula that says for any x, we want to give the result x times x. And that's going to be pretty useful in talking about lots of things that we're going to do in getting to calculus and so on. Well, so what are some examples of useful formulas? Let's say that we are driving along at 30 miles an hour, and we want to know how many miles will we have gone in 3 hours, let's say. Well, actually, there's just a formula, 30 times t, that tells us how far we will have got after t hours. So for example, if we say 30 times t and we say replace t with the number 5, for example, that would represent how far will we have got in 5 hours. And the answer would be 150 miles. So we've got this formula that tells us for any time t, we're driving at 30 miles an hour, how far will we have got in miles after t hours? And the answer is 30 times t. Well, another thing we could say is, all we know is the speed we're going at, 30 miles per hour. How do we work out from that how far we will have gone after t hours? Well, here's a way we could try and start working that out. Let's just say we're going to do our 5 hours here. We're saying 30 miles for each of those hours, 30, 30, 30, 30, 30. Let's say we make a, let's do this. Let's go ahead and make a plot, of a very boring plot actually here, of all those 30s. So it's like 30 miles for the first hour, 30 miles for the second hour, et cetera, et cetera, et cetera. And the answer, how far we will have gone altogether, is 30 times t. T is the number of hours here. Well, we can also think of that as the area of this rectangle. It's t across here, and it's 30 up, and the area is the one side times the other side, so 30 times t. Well, let's say we're a little bit more. Let's say that we go, I don't know, let's say we're going somewhere between 20 and 40 miles per hour for 6 hours. Okay, so there's the amount we went each hour. And now let's say we make a chart of how far we will have gone in each of those hours. So the first hour we went 22 miles, the second hour we went 31 miles. I mean, it's kind of a weird example because in a sense, we're just going constant speed for 1 hour. And then we change speed, we go at another speed. It's a little bit more realistic, maybe for airplanes, maybe for trains, I'm not sure, but it doesn't really matter. We're just saying for an hour we go at 22 miles per hour, next hour we go at 31 miles per hour. So the question is, how far did we go after all of that time? So we can work that out by just saying what's the total of those numbers. So for each hour, we went 22 miles first hour, 31 miles the second hour. So altogether, we went 170 miles. Okay, So that is also the area under this curve. If we add it up, that's a 21, height 21, that's height 20, 31, etc. So the area under this curve gives us the total distance we will have gone. Well, the big idea of calculus is to find a way to work out things like that area, just knowing what the formula for these values is. So let's take as an example, let's say, gosh, what could we do for our formula? We could just say, let's do a very boring formula. If t is less than 3, then 1, otherwise, let's say 2. Okay, so let's say we plot that. We say plot that for t from 0 to 5. Okay, so whoops, we should really have told it to show us a range. Let's go 0 to all there. Okay, and that's, I'm just going to tell it, because really I just told it what the value is for t below 3 and the value for t above 3. But let's say, let's see, I think I want to save that. Is that what I want to say? Maybe I want to save this. I'm hoping to get it to join those. Oh, no, I see. Don't exclude anything. So even though I didn't specifically tell it what to do when t was equal to 3, now I'm just telling it to join these values. So down here, from 0 up to 3, the value is 1, and from 3 up to 5, the value is 2. So what's the, if this was our speed, for 3 hours we go at speed 1, for 2 more hours we go at speed 2, the question is, how far did we go altogether? And the answer is the area under this part of the curve plus the area under this part of the curve. Now, to get really fancy, we can use a function called integrate, which is a calculus kind of function. We could just say, let's tell it to just work out the value here. So we say this, do that, and it will tell us the value is 7. So that is, we can work that out. That's, let's see, that's 3 times 1 plus 2 times 2. And that better be 7, and it is. Okay. Where things start getting fancier is when it's not so easy to just work out what the area is under this, because here, with this formula, it's a very simple kind of geometrical shape. Let's try a different formula. Let's say we have a formula. Let's just say we have the formula t squared, and let's just say we're going. It's a kind of unrealistic again, but let's just say this, for example. Let's say we're going faster and faster and faster at actually, let's just start off with something even simpler. Let's just say we're progressively going faster and faster. And that's, by the way, a realistic case, because when to increase your speed like that, to constantly increase your speed, is to have a certain acceleration. And there's a very practical case where that happens. If you drop something, the Earth's gravity is such that it leads to a constant acceleration of the thing you dropped. That's something folks like Galileo figured out. And in fact, it's the acceleration due to gravity is about 9.8 meters per second. So every second, one is going 9.8 meters faster if one's just falling according to gravity near the surface of the Earth. Now, it doesn't actually work that way because there's air resistance. If you drop things that are where the air is sort of pushing back on the thing, it won't fall as quickly as that. There was a nice experiment done on one of the late Apollo missions on the moon where there's no air, where someone took a rock and a feather and dropped them, and they do indeed fall at a constant, at the same rate on the moon. The rate on the moon is 1/6 what it is on the Earth. In any case, you drop something, its speed in a first approximation, ignoring air resistance and all those kinds of things, its speed will just increase linearly with time. So if let's just do this here. Let's say 9.8 times t, and that will say, so that's telling us after 3 seconds, we'll have a speed of about 29.4 meters per second, because every second, so at the first second, we increase up to, that should be, oh yes, I see. After 1 second, right, we're at 9.8 meters per second in speed, et cetera, et cetera, et cetera. Okay, so the question is, if this is our speed, how far did we manage to go after, let's say, 3 seconds? Well, let's see if we can work that out. So one thing we could do is to approximate this by a whole series of little boxes. So we could say here, let's say 0.1 or something here, and let's step plot that. And okay, so this is now showing us, oops, I should have made one small change to tell it how to plot this. And let's just say here, filling arrow axis. Okay, so this is now showing us in little steps what the, based on this function, this formula, 9.8 times t, each little step says for that, well, let's do it in steps of 1 to begin with. Okay, there it is in steps of 1. And now, so here, it's pretty easy for us to work out what the area under this curve is, which will tell us how far we will get, what the distance will go if this is our speed. So let's go ahead and do that. Let's just say we take this table of values, and there's our table of values. And at the very beginning, we haven't gone, because we only had 0 width at that place. So in the first moment here, let's say it's a second, we've gone 9.8 meters. In the second, during that second, we go 19.6. The third second, we go 29.4. Okay, so we can work out the total distance we've gone approximating things. We're approximating everything by just saying we jump from one speed to another at each successive second. And we can make it sort of more accurate by making our jumps smaller. So let's work out what happens with jump size 1, how far in that approximation, how far we would have gone. So let's work out that total. And okay, 58.8. Okay, let's reduce our jump size to 0.1. Okay. Ooh, that made a big change. What did I do wrong? Oh, I know what I did wrong. I didn't say to multiply this by the size of the jump, because what's happening is we're trying to work out the area, and each little rectangle here is not 1 unit wide, it's 0.1 units wide. So really what I want to do here is I want to multiply everything by 0.1, and there I get the result. So when I had width 1, I got that result 58.8. Let's say I go down to, let me go fill this in. Let's say I go to width 0.5, and I have to remember to put the 0.5 in here. Then I get, okay, 51. Let's say I have width 0.1. Okay, I have that. Let's say I go down to width 0.01. So I've got a lot of, if I go to width 0.01 here, you won't be able to see the, it'll just look like a continuous line. If I zoomed in really far, you might be able to see there's a little serrated edge there. But you can barely see it. So let's go to here to width 0.01. Okay, 44.247. Let's go down to even smaller width. Let's go down to even smaller width here. Okay, 44.1147. It's getting closer here. But you know what? Let's just make a picture here. So let's say we call this width W. We fill that in there. And let's say we make a plot. Let's see how we should do this. Well, we could make a plot. Let's say, how should I best do this? Well, if I just make a plot of this as a function of W, from W goes from 0 to, let's say, 0.1. I could try this. And I might want to do it a different way here. Let's do it a slightly different way. Oops, what did I do here? Oh, no, bad idea. Okay, well, tell you what, I am going to just do it like this. Instead of saying that table there, I'm going to say, make a sum of those. And oh, come on. Let's do this. Oh, there we go. Oh, okay, that's very wild. Okay, that, what happened here, oh, this is a very wild picture. Just reminding one that things aren't as simple as they seem sometimes. Okay, so what happened here, I know what happened here. We're seeing something very, very close to our value of 44. I shouldn't have done, I did something silly here. Let me see how best to do this. This may be somewhat confusing. There we go. Okay, this is confusing. Let me do it a different way. Let me do this a different way. Let's say we got this total here, and let's just make something where we say, well, what I'm trying to show you is that as this width W gets smaller, we end up eventually getting precisely some value here, about 44 point whatever. What's tricky is that at every specific size, you'll get a specific value. And this is showing us a plot. You know, if I made this plot and I said, show me a range of that plot with a range going from 0 to everything we get. Okay, what you'll see here is as our width W, we can even make it a bit bigger. We can go, our width W goes all the way up to 1. Okay, so what this is showing us, boy, this is a little bit complicated. This is showing us as our width, when our width is quite big, like 1, the value we'll get is somewhere on this curve here. As we make this width smaller and smaller and smaller, eventually, as the width goes to 0, the value that we'll get always ends up being this 44 point whatever value. So the point here is that if we go, let's try doing this with 0.000, put another 0 here. It's going to be very close to that value there. We go on, we put another 0 in here. Well, it'll get even closer. It'll be very close. At this point, it's 44.1. We're pretty sure it's 44.1. We do yet another 0 here. We'll get, it'll be really close to 44.1. So what we're doing here is we're saying we're trying to work out the area under this curve, and we're doing that by just breaking it into these little sections where we can explicitly add things up. What I tried to be very clever, but didn't work out so cleverly, to show you is as we change the width, just how do these numbers change, and it's a bit complicated. And that's because you're hitting kind of edges of those little square boxes, and you're differently hitting those edges, I think, as you change that width. So we don't have to look at this in more detail. All right. Now the question is, okay, so as we change, what is that number, that 44 point whatever it is number? So we could do the following. We could say, as we change, let's work it out. Let's take this result here, and let's say, what happens when we change that number 9.8? What happens if we call that A, for example? And if we make a table of those values with A going from, let's say, 0 to 5, and let's say just steps of 1. Okay, so this is now showing us how, as we change the slope of that curve, as we make the okay, so let me just show you this. If we say manipulate plot A times T t goes from, let's say t goes from 0 to 10 or something, and let's do this with a going from 0 to 5. And to see what's going on, we have to tell it to just make that plot for, let's say, from 0 to 50. Okay, so this, oops, I have to tell it to again. Okay, so now as we change a, we'll see the slope of this curve gets ever larger. So the slope tells us this, so this value of a, we could look at this. This is a value of a of about 1 point something. The slope is telling us for the amount of distance we go along here, how much will we have gone up? So if we say the slope is 1, then when we went along 10 units here, we will have gone up 10 units here. If the slope is 5, then when we went along 10 units here, we will have gone up 50 units here. I'm not drawing this to scale. I could as well. Let's just draw it to scale just so we understand what's going on. Okay, so this is now drawn to scale where we've got really 10 along that side, and now we go up, and that's the slope of 1 there, and this here is a slope of 5. Okay, so now that we know these slopes, now that we know what these are doing as we change a, now what we want to find out is how does the area underneath this change as we change this slope a. So let's work it out in this case here with our approximation to the area based on cutting it into little pieces. So let's go ahead and do this. Okay, let's make a picture of that. Let's say, oops, what did I do here? Table. Um, oh, what did I get wrong? Let's see. I am adding up these pieces and should have got, what did I do wrong? Yeah. Let's see, I better not be confused here. Let me see. We are trying to work out the area under this. What is going on here? Let's go back up here. We had said, hump, what did I do wrong? This is not supposed to happen. This is what I get for doing this completely cold, having never in my life officially taught about calculus or anything. But let's take a look here. What did we do wrong? This. Well, how am I getting? What is going on here? Well, let me show you that is giving us the total area under okay, what is happening here? This is each of those little pieces, and that, let me just see here. Let's make sure I was not confused somehow here. Oh, I know what we're doing wrong. Yeah, okay. All right, how embarrassing. Okay. So what happens here? Well, what we're trying to do is we're trying to plot what we had here. We're trying to work out what's the area under this whole curve. But now what we want to do is we want to, this is what we got wrong. My apologies. So what I was explaining here is if you have a certain acceleration, like 9.8 meters per second, this is plotting the speed that you will have achieved after some number of seconds. So now what we want to do is after that number of seconds you got to that speed, now you want to work out what's the total distance you will have got. So after each second, we know how fast we're going. And so in that second, so let's make a plot of this is telling us how fast we're going after each of these amounts of time. So in order to work out how far we will have gone, this is what I worked out here by working out the total of this. That's an approximation to how far we will have gone after that. The first second, let's say we're going at 4.5 meters per second. The second second we're going at 9, and so on. And so in a first approximation, we just say first second we go that speed, the second second we go that speed, third one that speed, fourth one that speed, and so on. And so if we want to work out how far we will have gone after all of that time, we just add those numbers up. But if we change and this is okay, but I should have shown you here. Okay, let's restart this a bit. Okay, let's review again what's going on. Okay, so remember, at the beginning we were talking about if you go at a certain speed for this hour, for example, you got this speed, this hour, you got this speed. We're trying to work out what is the total distance that you will have gone after all this time. And for that, for each hour, you add up the distance you went during that hour, which is your speed times 1 hour. So if it's 30 miles per hour, it's 30 miles in that hour. Okay, so now what we're saying is that if you are progressively accelerating, then these speeds will go up. So then what we would get, for example, here is we would say we would get speeds that go up like this. And so at the end of that time, you're going at the speed here. But to work out how far you will have gone, you have to add up, you have to work out the area under this curve. Okay, so how do we work that out? Well, at each of those steps, this is telling us at each of those steps how fast we will go during each of those steps. And so the distance we will have gone after all of these steps is this total. But what's tricky is that what we really want to know is how far we will have gone after, not after all of the steps, but after each step, how far will we have gone? And so for that, what we're doing is we're accumulating these values. So what does accumulate do? So let's say we say something like A, B, C, D. It's saying A plus B, A plus B plus C, A plus B plus C plus D. It's progressively adding on the next number here. So what we're doing here is we're saying for every one of those seconds, we know how far we went in that second. Let's add on how far we went in that second to how far we've gone previously, and let's keep adding that on, and that will tell us how far we go altogether after each of these seconds. So we just did that here. So let's take a look at what that looks like. So if we say, let's make a plot of how far we will have gone. Okay, that's what it looks like. So if we plot how fast we will have gone after this each amount of time, this is what we get. It's a straight line. It just goes, because we're accelerating at a constant acceleration leads to a speed that just goes up in this straight line. But now we're trying to work out what is the total distance that we've gone. So up to this point, we started off going at this speed, then we went faster, faster, faster. When we get to this point, we went slower at the beginning, faster at the end. How fast did we go altogether? How far did we go altogether? How far did we go altogether when we got to this point, we got to this point, and so on? That's the result that we get. So what is that? Well, if we say this is 9.8 times t, it turns out there's a formula for this curve. That curve turns out 9.8 times t squared divided by 2. And if we plot that, so let's say we're not accumulating it anymore, we're just plotting it, we'll find out we end up getting the same curve. Yeah, I should have multiplied by 0.2 here to get the actual same curve. Because that's the width of each of these little pieces. So the idea is you're working out always the area under the curve. And the question is there a formula for the area under the curve? And the big idea of calculus is, yes, you can work out a formula for something like the area under a curve. Now, actually, it goes, that's the idea of computing integrals, is the idea of going from a formula for a curve to the formula for what's for the area under the curve. And so let's do that. We can just ask, what is the integral of, let's say it was 9.8 times t? What's the integral with respect to t? You can write that as integral 9.8 times t and then dt. That's the somewhat crazy notation that has historically been used since, well, the end of the 1600s to represent things in calculus. That integral sign is kind of an elongated S that really stood for sum. And it's just like we were adding up all those little boxes to find the area. This was kind of a notation made up by Leibniz that was kind of well, it's roughly a sum. And then this dt, remember, we kept on having to multiply by the width of the little boxes. That dt says it's the difference in the t's, it's the width of those boxes. So this is kind of the notation for something which doesn't talk about boxes anymore. It just talks about how you take one formula and you compute another formula from it. So sort of the big idea of working out this integral is it's working out the area under a curve where the curve is represented by a formula, and what you're going to get out from the integral is a formula for the area under that curve. Now, if you just draw, let's see, we could just, we could make some curve. How could we do this? Let's just make, how about we do this? I'm gonna use something fancy here, but let's just use that to get a result here. Let's say, let's do this. Let's do that. Okay, so let's make this thing here, and I'm going to use this. This is kind of like a function that we can set up that I just sort of picked it. Let's take a look here. Let's go. Let's see what this looks like. There we go. Okay, so I just made a function. Oh, I should have gone from maybe 1 to 10. Let's make sure I can go from. Oh, I see. Yes, okay, let's go from 1 to 10. All right, so this is a function that I could have like scribbled. I didn't actually scribble it, but it's as if I scribbled it. So this is telling us at every value, it's telling us for every value, x value down here, it's telling us the value of this function. And so we can think of this as being, maybe this is like the speed of an object as a function of time, and the thing is accelerating here, and then it decelerates here, and so on, wiggles around. And so if we want to work out how far will the object have gone if this is at speed as a function of time, then what we have to do is work out the area under this curve. And if we wanted to, we could approximate this. We could do the same trick we did before. We could start saying, take this function here, and let's make I could do the exact same thing I was doing before. I should have called that variable t, let me call it t. And I could say, make this as a function of t from 1 to 10 in steps of 0.5, let's say. And then let me say, make a plot of those. Okay, so this is now an approximation to this function where I just evaluated it at a bunch of fixed points, 0.5 apart. So this is, if I were to plot, let me go ahead and do that. And the most recent thing there, and let me plot them together. That is incredibly uninformative. My apologies. Let's see, how do we get this to look better? You can roughly see that they agree here, but I think we need a, let's do a better version of this. I know how to do a better version of this. Let us go ahead and say, well, you can kind of see that they have the same structure. There's a little peak there, another peak there, and a trough there, and so on. Let's just believe for now. Oh, I see what I did wrong. Yeah, same mistake. I keep on leaving out that dt. I need to put this in here. Oh, actually, no, I did something else wrong. Yes, what I should have done is this. Oops, didn't actually get it right. Oops. Okay, let's try this again. And let me just make this, let's say, plot style red. Okay, now I'm going to combine these two together. 28 and 32. And now you can see that that thing with the little, with kind of the rectangular pieces approximates that function that I showed you before. Okay. So now, for example, I could work out the area under this curve. I could work it out by getting all of these steps here, and I just work out the sum of all of these values for all these steps, and I have to not forget the dt. So let me go ahead and do that. So I'll make this object, this thing here, just represents that function that I kind of scribbled. So I'll do that. I'll multiply by whatever dt. Let's use 0.2 here, and let's make a table from t equals 1 to t equals 10 in steps of 0.2, and that's going to be oops, that's the table of values. Now what I want to do is find the total of that, and that's going to be the area under that curve, roughly. Okay, let's try the following. Let's use the fancy method, and let's say integrate there. T goes from 1 to 10, and that's all we need to tell it. And now let's see what that does. Oh, look at that. So we didn't get quite the right answer here because probably 0.2 isn't quite small enough. You can see it's not exactly following the curve there, but we got something close to what doing this integral. Maybe I can just to make it look fancier, I can do this. I can say integrate this. Oh yeah, let me make it look really fancy, and let me tell it we want to integrate it. I never use this, but anyway, let me go ahead and do that. Let me say I want to integrate that between 1 and 10, and then I say dt. and I get that result. Okay, so here, if we make our approximation a little bit better, so instead of using 0.5 here, let me go ahead and just fill this in here. And instead of using 0.5, let's use 0.05. And let's see how that does. Okay, we shouldn't have even used 0.05 because we can barely see one. The curves are just right on top of each other. Let's say 0.1. It's still really good. Let's try 0.2 example. Okay, there we can see it's not quite there, but it's really close approximation. So now we can let's use our point. Let's use, what was this? This was, okay, that was actually using 0.2. So that was using that approximation. Let's use 0.01, which is going to be really, really indistinguishable if we just look at it by eye. And now we'll get 44.5207. And here we get, doing it in the official way, we get 44.46. Okay, let me just to prove this really does work, let's go ahead and make this 0.001, 44. Okay, it's getting really close here. And it is going to get to the right answer in the end. But so what that's telling us is that this magic function, integrate, is managing to figure out from the formula for a curve what the area under that curve is. And that was the big trick, which was discovered in, well, basically the 1680s by Isaac Newton and Gottfried Leibniz at more or less the same time, with some complicated interwoven story between the two of them, which that you could just work out from a formula. You could do things like work out the area under that curve. So let's work out. So let's say we have t squared, for example. We could work out what's the integral of t. It's t squared over 2. That was the thing that went from the straight line, the t, to a t squared. And then, for example, we could say what's the integral of t squared? It's t cubed over 3. And actually, we could say if we just integrate t to the n for any n, this might give a weird answer. Oh no, it doesn't. It tells us it's t to the n plus 1 over n plus 1. So these are rules about doing integrals. Now things can get much more complicated. For example, let's say I do an integral of, let's say I do, I don't know, 1 over t cubed minus 1. So that's a sort of a reasonably straightforward looking let's see. That's a reasonably straightforward looking function. Let's work out its integral. Oh, it's kind of a complicated mess with arctangents and things like that. So this is where calculus gets complicated, is that it turns out even when the formula for the original curve is something quite simple, the formula for the integral, the area under that curve, can be something quite complicated. And that's kind of one of the difficult things in calculus, is being able to go from what could be a quite simple formula here to this much more complicated formula here. We'll talk a little bit more about that in a moment. But first of all, I need to explain to you the other sort of big story of calculus, which is derivatives. So I talked to you about, given a particular curve, we're working out the area under that curve. Well, there's an opposite operation, which is what's the slope of the curve? And if we say, when we work out the area under a curve, we're just continually adding on more stuff. For every little piece of where the curve got to, we're adding something on that represents the extra area added by adding that piece of the curve. Okay, so what happens if we want to go the other way? If we want to go from the area back to the original curve, what we now have to do is we have to say, well, what would we be adding on at each stage to get from one result for the integral to the result for the integral for the next, at the next position? And the answer is we'd have to be adding, if we look at the slope of that curve, that's telling us how much we're adding on as we move across the result for the area. So the big result is the slope of the curve. If you have a curve that represents an area under a curve, if you find the slope of that area under a curve, you get back the original curve. Okay, let's do an example of that. So let's say we have our x squared. So remember that x squared was what we got by working out the area under the curve, just under a line. T squared over 2 was what we got by working out the area under the curve t. Okay, so let's plot this from 0 to 10. Okay, it looks like that. Now let's try and work out what is the slope of this curve at every position, right? So what is a slope? Well, a slope is if we put a line to approximate this curve, what would that line look like? So for example, I'm sure we can, there's a better way to do this, but let me just show you here. If I say plot this, and then I want to plot, well, let's see how to do this. What's the best way to do this? I'm going to, well, here's one way to do it. If we want to know, what we want to know for this curve is, for every distance we go across, how much does this curve go up? And so, for example, let's say we make a table of the values of t squared over 2, t going from 0 to 10. Let's say, well, let's just do it in steps of 1 here. And those are the values of t squared, with t being 0, 1, 2, values of t squared over 2, 0, 1, 2, etc. Okay? So now, to work out the slope of this curve, we can at least approximately work it out by seeing, oh, but by the, let's go ahead and plot those along with that original curve. Okay, so let's say we want to plot, say we take this and we want to say show that with this table, and at each place we want to plot t and t squared over 2, and we want to do that. And just for the sake of, let's say we say a list plot, and then we want to say, let's make them red. Okay, all right, so those are our values plotted along here. So to figure out the slope of this curve, we can just say, what's the difference between that value and this value? And how far do we have to go to get from that place to that place? And that will give us the slope. So let's go ahead and do that. So we can just take these values, and the slope will be, for example, at this place, at the 24.5, it's 32 minus 24.5 divided by the distance we went on the x-axis, which is in this case 1. So we can work that out. Conveniently, we have this function called differences, which will go ahead and work out the differences between those numbers. And so these will be the slopes. So this will be saying so that's telling us the slope of the line from here to here is whatever that corresponding number is. So let's go ahead and work out these differences. Let's plot those differences. Fancy that, it's a straight line. So it's telling us that the successive differences of this t squared curve are just like t. The successive differences of t squared are just the line t. Well, actually, let's do that in a bit more detail. Let's say we go, let's make a table of t and t squared over 2, and let's make that from t goes from 0 to 10 in steps of 0.2, and we get all these results. And so now here, let's look at the slope here. Okay, so what is that going to be? So that's going to be, let's do it very much by hand. Let's say 13.52 minus 12.5, and that's that. And then we want to say that's the difference there. Then we want to say divide by 5.2 minus 5. That's the difference of how far we had to go on the x-axis. and we get the result 5.1. So interestingly, that's basically our position t. So this is telling us that the slope of this curve that we drew, the t squared over 2 curve, the slope of that curve at the point t equals 5 is about 5. Now, okay, so in the way this gets done in calculus, one might say that x is given by t squared over 2. We might say that something like, I don't want to type it in because it'll make it actually set that, but let's say x is t squared over 2. And now what we want to say is how much difference is there in x for every small change in t? And so in the slightly crazy notation of calculus, we have this dx divided by dt, or it looks like dx over dt. And what that's representing is we take the difference of the x values, which is I should have called it. Let me try to make this less confusing, because let's say this is the x-axis and what's on the vertical axis is the y-axis. So let me redo this and let me talk about that. Let me say what's on the x-axis is x, what's on the y-axis is, so this, whoops, isn't a good idea. Okay, so now I'm going to say that the difference of y values, let's do it for here, for example, the difference of y values here is the difference of those two values. So 6.48 minus 3.6, that's the difference of the y values, divided by the difference of the, sorry, I meant between, sorry, I should have said between this and this. So what I'm doing is I'm working out, and that when I copied it out, it got much messier there, but the difference of the y values is 6.48 minus 5.78, divided by the difference of the x values, which is 3.6 minus 3.4. And it's very close, it's 3.5, which is essentially the value of x here. So that's why in calculus you often write dy divided by dx, because that's representing the change in y divided by the change in x. This notation is super confusing. When Leibniz first wrote down this notation, he immediately said, people will think you can cancel the d's, it's really confusing, and it's been confusing for 300 years. In Wolfram language, we have a slightly different notation. We just say capital D, and we could say capital D of x squared over 2, what's that equal to? And that tells you that's the slope of the curve, the so-called derivative of this function x squared over 2, the slope of the curve corresponding to x squared over 2 with respect to x. So that's the y value, and this is taking those little tiny differences divided by little tiny differences of x, and the result is x in this case. So in general, if we work out, let's take the integral. Let's do the integral of x to the 6th with respect to x. Okay, it's x to the 7 over 7. Now let's take the derivative of that very thing. Of that thing, let's compute it here. Let's take the derivative of that thing with respect to x. Ta-da, we get back x to the 6th. So when we work out an integral in the area under the curve, and then we find the slope of the curve again, we get back the original curve, which in this case we had being x to the 6th. Now, what is really cool about calculus is you can do this purely symbolically, just in terms of the formulas. I could always go back and I could work out all the numbers, and I can take differences of numbers, I can work all that stuff out. But the thing that was the big trick discovered in the late 1600s was that you can do this just with formulas. Okay, well, let's look at how that works for some other formulas. Turns out finding derivatives is actually quite easy. It's very systematic. Finding integrals is comparatively much harder, because with derivatives, it's extremely systematic how you work out a derivative. You have certain formulas, but well, let me show you this sort of the key fact. I guess let's do the derivative of some kind of complicated function. I don't know, let's do the derivative of my function 1 over x cubed minus 1. Let's show you that. That derivative is 3x squared over this. Let's work out the integral of that result. Let's do the integral of that with respect to x. Ta-da, x cubed minus 1. Now, it just turns out that the algorithm to find a derivative is very systematic and straightforward. The algorithm to find an integral is not as straightforward. The only thing we know about any integral is that it better be the case that if we differentiate it again, we find its derivative, that it gets back what we started from. So that's a way to it's kind of like what happens when you multiply numbers together and you can get, and when you can multiply numbers together, and it's pretty easy to do. But if you want to factor those numbers and figure out what numbers you could multiply together to get the number that you got got that final result, that can be quite hard. So if I multiply those two numbers together, I get that result there. But knowing how to go back to what I get, my original knowing how to get back to those original numbers, oh, that one turned out to be a prime. So we could immediately see that we got back to that number. But working out how to factor them is much harder. Now, turns out that, as is often the case with computations with integers, where you're just working out multiplying and factoring and so on, those turn out to be fundamentally harder than computations involving things like these kinds of formulas. They're dealing with formulas is a more difficult thing to get a computer to do, but it is something where once you've taught the computer to do it, it is ultimately probably easier. I say probably because there's some pieces that still aren't quite known. It's probably easier than doing this thing with integers where you say, I multiply these integers together, let me factor them. It's probably harder to do that factoring than it is to do these integrals where you're saying, I've taken the derivative and now I want to integrate again to get back to what I started from. But anyway, so let's take a look at some kinds of derivatives and integrals and so on. Let's take a look at what kinds of things we can do. And let me actually tell you why it's easier to work out derivatives. And I think I can tell you. And it all has to do with a thing called the chain rule. Okay, so let me see how I can explain this. We talked about something like x just standing for any number. And people figured out the idea of algebra and things like variables like x standing for any number. That was figured out kind of in the 1400s to beginning of the 1500s and so on. That was kind of the introduction of algebra. Well, much later, much later, really not until the 1800s, late 1800s even, people started thinking about the idea of something like f of x, where f is any function. So for example, here we might say there's a particular function that it's 1 over x cubed minus 1, for example. But let's say we deal with any function, f. We're not saying what that function is. That function could be x cubed. That function could be 1 over x cubed plus 1, all those kinds of things. It could be anything. We can think about that function as transforming x to some value. So in Wolfram language, that's actually super clear the way that's written out. You just say function f, and you're naming the thing that you're putting in there x, but there's a blank, which means you could stick anything you want in there. So the way it works in Wolfram language, you could say something like, I don't know, 1 over x cubed minus 1 here. And that tells us for anything that we stick in there, if we put in there 4, we'll get back a result like that. If we put in there w, we'll get a result like that. If we put in there a plus b, we'll get a result like that. If we put in there, and this is now getting just crazy, let's say we have a picture of an elephant. Oh, this is going to do something really wild. No, let me not do this. This is going to be amusing, but really not to the point. This is going to actually deal with every pixel that way. Let's see what happens if I there we go. Okay, let's just say I say, oh, I don't know. I could put in, let's just put in a little picture of a wall. There's a good, nice emoji for you. It can be absolutely anything. All it does is it says, whatever I see there, I just am transforming it to 1 over the thing minus 1. And okay, so now the question is, what's, for example, the derivative of f of x with respect to x? Well, the answer is, we know what f of x is. It's 1 over x cubed minus 1. And we can work out the derivative like this. We can do the integral as well. We could do that. Because we told it f of x for any x, f of x is this here. Okay? But let's clear our definition for f now. And let's see what happens if we just tell Wolfram language to find the derivative of f of x. Well, we're not telling it anything about f. What's it going to do? Well, it's going to tell us that the derivative is f prime of x. F prime is an object that is kind of a symbolic derivative. Just like x symbolically stands for any number, f of x, the f, symbolically stands for any function, anything we could do. It could be 1 over x cubed, it could be 1 over x to the 4th, it could be anything. And we represent the derivative of that symbolically as f prime. Okay, but now there are a bunch of rules. So for example, let's say we said f of x squared with respect to x. Turns out the answer is 2x times f prime of x squared. Well, we can go and let's do this. Let's put in here x to the 4th here. Okay, it's 4x cubed. Okay, well, here's an interesting fact. That if we find the derivative of x to the 4th on its own, it's 4x cubed. What's happening here is there's a chain rule that says to work out the derivative of a function of some other function, you just multiply together the derivative of all the pieces, basically. And you can kind of think of it literally like a chain. You have a chain, it's hanging down. You've got the first rung and the second rung and so on. Each piece of the chain, where it gets to depends on where the previous piece of the chain was. And so if you say, well, what happens when I make a small change to the position of when I'm making successive small changes to the slope of the chain, what you'll find is that the position of the end of the chain is what you get by multiplying together all these various slopes and filling things in. It's a little bit more work to see how that works for the mechanical case. But the thing that is significant for derivatives, if I say f of g of x, then turns out, whoops, I should say with respect to h, shouldn't I? Then that's the result. The result is that we can unwind this derivative and we can keep going. We can keep unwinding it. And there's just this formula for the unwound derivative. And turns out this that means that there's a very systematic way. If I show you some, because I can think of any function, we actually talked about that a year ago. If I think about a function like x times, I don't know, 1 plus square root of x all squared, for example, I can think of that in Wolfram language. It's very clear. I can think of that as a nested sequence of functions. It's a times on the outside that's multiplying together, of a power, that's the x squared, of a plus, and then a 1, and then another power on the inside. So to work out this derivative, what we're doing is we're just using the chain rule, and we're unwinding all those different things. And for each particular function, we just have a table that tells us what the derivative is. So we know the derivative of the power, what that is. I wonder if this works. Let's see. If I just say, let's just see what happens. If I say, I wonder if I could do this. This is a know your system. I wonder if that works. Oh, yes. Wow. Okay. I think I might have to say, oh, okay, never mind. Let me not do this. I'm playing here. But in any case, the basic point is the reason it's easy to do derivatives is that any function you write out, anything you write, any sort of function of x that you write down, you can always think of it as this nested sequence of known functions like plus and power and times and so on. And as soon as you know their derivatives, you can just use the chain rule to find out the derivative of the whole thing. Okay, so that chain rule idea, by the way, in modern machine learning, there's sort of a big deal because when you have successive layers in a neural net, it's like applying successive functions to the original input you gave to the neural net. And if you want to know, if you want to say, well, how do I have to change the weights inside the neural net to have this change in the output, then it turns out you can essentially use the chain rule to work out sort of you can invert, you basically use the chain rule to know what was the individual contribution, what is the final change, and how are their contributions to that final change from each of the layers. It's a bit fancier than this, but essentially the modern machine learning in this method called backpropagation, it's a giant using the chain rule story. It's sort of a modern application of calculus. As it turns out, you probably don't need all the stuff of calculus. I actually worked that out very recently for machine learning, but that's a different story. In any case, when it comes to talking about calculus, we have this chain rule for derivatives. There is no similar result for integrals. If I say, what's the integral of f of g of h, it's very complicated. There's nothing general I can say for any functions f, g, and h about what that integral is. There are particular formulas. For example, if it so happens that I have something where I'm saying I've got f prime of x times f of x, I think that in that particular case, because basically giving you on a platter sort of chain rule like stuff, you can work out the integral for general f. But most of the time, you can't do anything like that. So let's try something like this. Let's say we do a derivative here, and then let's say we integrate that with respect to x. Okay, now we're seeing something tricky again. So look at the original thing that we worked out a derivative of. There's the original function, and then we took a derivative, and then we integrated that again. Well, we're supposed to get the same result, but it doesn't look the same. So this is, again, how things get tricky, because in algebra, one of the things that happens is that there are different ways, but when we're dealing with numbers, you write 5, and there's just one way to write 5. If I write, let's say I write 5 over 10, okay? That turns out there's more than one way to write that. I can write 5 over 10, or I can write 1/2. When it comes to algebra in general, it's very common that there's more than one way to write things, that it isn't just, it's that there's, so in algebra, for example, I can write x plus 1 times x minus 1. That's one thing I could do, or I could say expand that out. Well, let's do it separately here. Let's say expand that, and I'll get x squared minus 1. It's the exact same. The values will be exactly the same for any x. X plus 1 times x minus 1 gives exactly the same value as x squared minus 1. It doesn't necessarily look the same. And that gets tricky when you're dealing with calculus, and when you have something like this and you get back a result and the result looks different. So let's check if these are actually the same. So we've got, let's just work out, I'm just going to do, well, let's just say this thing here, is that thing the same as this thing here? It's going to say, initially, it's probably going to say, I don't know. Okay, it's going to say, I don't know. But let's say we simplify both sides. It's going to say, yup, those are the same. Because what happens is if I say simplify this, I wonder what it's going to do. I don't know what it does for this. Simplify is a very kind of, it's sort of a heuristic function. It's just saying, give me this in a way that a human might say it's the simplest form. And in this particular case, it was the original form I typed in, and it verifies the derivative and the integral are the same. Okay, let's take a look, just for fun, at some at some integrals. I'm going to try and make this up because I don't actually know what's possible. Let's try something like this. I wonder whether we can find the integral of that. Well, let's do the derivative first. The derivative, that's easy enough to find. Now let's try the integral. He's living dangerously here. Oh, not too bad, not too bad. Okay, there's a little bit of an exotic function log in here. We'll talk about that in a minute, but let's just try, ooh, what can we do here? We could say, okay, I'm going to make it really mean here. I'm going to say 1 plus the square root of x inside the square root. So let's see whether it can even do this. Ah, we could do that. Interesting. All right, let's see. I wonder what happens if I change that 1 to a 2. Okay, it's getting a little bit more exotic. There's logs and things in there. Let's just, I'm going to explain about logs in a minute, but let's just put a log on the top there. Ugh, all sorts of horrifying stuff going on here. And notice there's a thing called a polylog that started showing up here. Actually, let's try and simplify this. It can be quite hard to simplify these things. You can go crunch, crunch for a while. Okay, couldn't manage to simplify it. We can kind of show it in the traditional way it might be shown in a math book here. Didn't really change it much, except that that polylog is now Li sub 2. They don't teach about polylogs in, I don't think you'll run into polylogs until you get to graduate school math, or actually some graduate school theoretical physics. But in any case, this is, but what's interesting is we started off with this function that looked fairly simple here, but the integral is something quite complicated. And this is as I say, it's a very common phenomenon that the integral is a complicated thing to find. And how do we find integrals like in Wolfram language? Well, turns out that many of these functions, well, first of all, there's kind of a whole zoo of functions. There's multiplication and addition and powers, and then there's things like square roots. And then there's things like logs, there are trigonometric functions, this is an arc hyperbolic function, inverse hyperbolic function. There's a whole zoo of functions. There's like 400 of these things, which are sort of common functions that people have found useful in doing mathematics and mathematical physics and other kinds of areas. So there are all kinds of things. There are Bessel functions, there are elliptic functions. There's a whole zoo of functions. These functions usually kind of showed up because they were the solution to some kind of equation. Just like a square root, in a sense, is a solution. The reason we care about square roots is because if we're trying to solve the equation x squared equals 9 for x, well, x squared equals 3, solve it for x. X is something we call the square root of 3. It has a numerical value. We can work that out. But we can represent it as that's the square root of 3. It's the solution to an equation. Well, there are much more exotic equations. We could say, let's try and solve, what's a good example? Here's an exotic equation. So let's try this equation here. Not sure if we can solve that. Yeah, we can. Okay, so it's tricky because there actually are many solutions. Just like here for x squared equals 3, there were two different solutions. Either x is minus square root of 3 or plus square root of 3. Here, they're actually an infinite set of solutions. It's all rather complicated, but the basic solutions involve this thing that's a function that we introduced actually called product log. It was introduced in the 1600s by various people, but we call it product log. And it's a function that is a much more exotic function here that you need in order to represent the solution to that equation. And this is it's a pretty common thing that when you are saying what value of x satisfies this relation, that answering that question is more difficult than just evaluating, well, what happens for that particular value of x? So inverting things to solve something tends to be more difficult, and it tends to go from one kind of mathematical function to another kind of function. Let's try this. Let's say solve x equals, no, let's just try a equals 2 to the x. Let's solve that for x. Oh gosh, a bit complicated here. Sorry, let's do this. Let's try this. I think this will make it simpler. Okay, so yeah, so this is basically saying x, if a equals 2 to the x, then x is this thing called log of a. Let me oh, I can talk about logs for a second, and then that will lead us to another kind of interesting thing. But I just wanted to emphasize again this fact that integrals are hard to do. Derivatives are correspondingly much easier. So if I take that thing there, it's a big mess, and I say find the derivative of that with respect to x, okay, it'll still be a big mess. But if I say full simplify that, look at that. Isn't that nice and simple? That was the thing we started from. And again, it's lots of technology to figure out how to do that simplification. But this complicated thing here can also be written like this. And that was the original form we started from. So that's so maybe I could tell you a little bit about how Wolfram language actually does integrals. The thing is, in this zoo of functions, there are functions that represent all sorts of integrals. So for example, a famous one is the integral of x to the a times 1 minus x to the b. This was always my favorite integral when I was a kid. Let's see if we can do it. Don't tell me it says something complicated about this. Oh boy. Okay, it has various conditions here. Okay, well, this is in terms of a rather exotic function called the gamma function. That integral looks harmless enough, but it's actually pretty hard to do. So if I fill in particular values here, x is 2 there, and b is 3 there, I get a particular value. But the general case for arbitrary a and b is somewhat more complicated here. And it turns out that this is an example of an integral. Once you know that answer, by differentiating that answer, you can get all kinds of other integrals. So just to give you one example here, if you differentiated this, let's do this here. If you, this is going to get complicated really quickly. But if you differentiate that with respect to a, oh yeah, and I have to do, yeah, this is again, a lot of things are going to get complicated here. But I'm just trying to get you a sense of what happens. What's tricky is what happens when a equals 1 here. But in any case, the yeah, what basically what you can do is once you know this result for all a and b, turns out by doing various tricks of integral of differentiation and things like that, you can turn that result there into a result for lots of different kinds of integrals. And turns out in the very general case, let me try something here. I'm going to do some very exotic integral here. I'm not sure I can figure out what it should be, but I'm going to try, oh, I don't know. Let's try something like this. I have no idea if this can be done. Cannot. Right, well, let's try getting rid of one of these. No. Okay, what does it mean when it just returns without being able to do it? The answer is, what it means is there are no standard known mathematical functions in terms of which this result can be stated. So in other words, if I were to work out for particular values, let's say a equals 2, c equals 3, okay, oh, look at that. That's the kind of thing I wanted. Yes, here we go. So that's a very innocuous looking integral, although it involves functions we haven't talked about like sine and log. But look at all that exotic, weird stuff involving hypergeometric PFQ functions, all this kind of thing. It's very exotic. And those are the things you need in order to represent that integral. But it turns out that once you're dealing with these very exotic functions, you can represent a very wide class of integrals just in terms of one of those functions. And then what is the big effort in integration in Wolfram language, for example, is going from essentially giant industrial strength formulas that give you pretty much any integral that anybody would ever be expected to do in a calculus course can be done basically using a formula in terms of hypergeometric functions and other exotic things like this. But if you handed in that result as the result of your homework, people would say, what on earth is that? You know, what it doesn't, it's not the result of the integral. Well, it is the result of the integral. It's just that it's in terms of functions that aren't terribly familiar. And so the big effort then is to simplify those functions. So if I take that really exotic hypergeometric PFQ function and let's say I evaluate it for a particular value 3 here, okay, it didn't manage. But if I say, what's the numerical value of that, let's say to 50 decimal places, it's just going to compute it. It's just a number. And the issue is there a way of taking this thing here, and I have no idea if there is, this thing here for value x, for example, oops, that thing there for value x, is there a way of representing this in terms of simpler functions, more familiar functions? Okay, it doesn't think there is there. Let's just try one last ditch effort. No, it couldn't do it. I wonder whether for a particular value of x, whether it has a hope here. Let's just see. Let's see. Let's put in the value 2 here. Nope, it didn't have a hope. Let me try making it a bit simpler, give it an easier time. Let's try doing something like this, because I know something about what those things mean. Okay, there we go. All right. So there, that slightly simpler, very general function could be simplified to more familiar functions. Not that these are terribly familiar. The cosh integral function and so on is not a a very familiar function, but it's somewhat familiar. By the way, so this is the kind of thing. So the way that we do things inside Wolfram language is we're using sort of these big sophisticated formulas that work out lots of integrals in terms of things like hypergeometric functions, and then the big effort is in figuring out how to simplify those to much more familiar functions. Well, maybe I can talk a little bit about some of these more exotic functions, because they're kind of a thing that comes out of the whole calculus story. I want to talk about those. I also maybe can talk a little bit about differential equations. Just as let me give you some examples here. So just as we can take some equation, like we can say, you know, solve x squared plus 5x plus 1 equals 0, solve that for x. So here, and we get some results, that's the quadratic formula. What happens if we have something that says the derivative of f of x with respect to x? What happens if we say that's equal to x, for example? Okay, so we have f prime of x equals x. What's the analog of solving that equation? Well, it turns out there's a way of doing that. This is what's called a differential equation. It's an equation about a function, about the derivative of a function. So we say f prime of x equals x. We can say d-solve that for f of x with respect to x. And what we'll discover is that if f prime of x equals x, then f of x is x squared over 2 plus a constant. That's a tricky thing. Let me explain that for a second. If we find the integral of let's say, x squared with respect to x, this is an integral. I know I don't know very many integrals. I've used a computer for way too long to do integrals, so I don't really have to, it's not really super useful for me to remember these, but that one I know. Okay, so that's the integral. And I can differentiate that again, and I'll get x squared. But let's say that I take that result and I add 75 to it, okay? Well, the derivative of that is also x squared. So pedantic calculus books will tend to say, when you state the integral, you always have to say plus a constant. Why does that make any sense? Well, the answer is that the derivative remember, is finding the slope of a curve. But you can move that whole curve up and down any way you want. You can add a constant value to everything in the curve, and you won't affect the derivative. And so if you say, well, the integral is the area under the curve, you could say, well, I'm going to add an arbitrary amount to that area. It won't affect the slope of my area function, and so it won't affect the derivative. And so I can say that the integral has an arbitrary constant. That arbitrary constant is more important when you're dealing with a differential equation, because differential equations often are used to represent sort of physical kinds of things. And you're saying something like, well, as soon as it's going, the f prime, let's say f represents the position, the change of the position is equal to x. But let's say we fill in a condition that says that f of 0 is equal to, let's say, 17. Okay, now we solve that equation, and now we get a definite result. There's no plus a constant. We anchored this by telling it that f of 0 was 17. And so then the solution to that equation is some definite thing that doesn't have this arbitrary constant. But if we didn't give it that initial condition, as it's called, then we would to really say what the possible solutions are, we have to say plus an arbitrary constant. Okay, so differential equations are the analog for doing derivatives that ordinary polynomial equations are. It's like find the x that satisfies this equation, this thing equals 0. Here it's find the function f that satisfies f prime of x, or the derivative of f with respect to x is x. Okay, so differential equations are hard because they're hard like integrals, because actually this differential equation is really just computing an integral. There are differential equations that do more than just computing integrals. And differential equations are kind of the stuff of, well, originally in mechanics and physics, the big discovery of Newton, and, well, primarily Newton actually, was that differential equations can represent sort of the mechanics of things in the world. They can represent how position is related to acceleration. They can represent the motion of things under gravity, et cetera, et cetera, et cetera. They are a way of representing kind of mechanical processes. And then in the 1700s, it was discovered that, yes, well, differential equations apply to other things as well. Like, well, actually, by the 1800s, it was known they applied to fluid flow. They applied to electrodynamics, the study of electricity and magnetism. That was the later 1800s. And then in the 1900s, the early 1900s, it was, and they applied to quantum mechanics as well, and then to lots of other things. So differential equations became kind of the stuff of mathematical physics. Also, in a few areas of where one can do those kinds of analyses in biology, like in things about hormones and so on, endocrine system, you can work things out involving differential equations as well. And differential equations became sort of the raw material for a lot of the applications of mathematics to engineering, and that's sort of the thing one's solving all the time. Well, just to make things more, so just to give you a sense of differential equations, let me write down another differential equation. Let's say it's x plus f of x here. Let's see, does that have a solution? Okay, that has a fairly simple solution. Let's say I'm going to live dangerously. I'm going to say f of x squared here. And horror. Okay, a very complicated solution involving these things called Bessel functions, invented for studying the motion of the moon back in the 1800s. But in any case, so again, it's with differential equations. Even a pretty simple differential equation can wind up with a pretty complicated solution here. It's not quite as straightforward as with integrals, where you can just differentiate it and see you got the right answer. But by the way, you might also ask the question, well, what about integral equations, where you say something like this equals something or another? That's actually integral equations. They do show up, but they're a lot less common than differential equations. It's a lot more common to know that the rate of change of something, or the slope of a curve, which is the rate of the change of the thing, is proportional to something. That's a common thing to know in the world. To say the total accumulated amount of something is equal to something is less common. Integral equations do show up in light propagation and scattering theory and in a bunch of other places, but they're much less common than differential equations. So, okay, let's look at some differential equations. Here, let me show you a famous, super famous differential equation. The equation f prime of x equals f of x. Solve that for f of x with respect to x. Okay, the result is e to the x. So what that's saying is that's a function, f, that has the form that the derivative of the function is equal to the function itself. And turns out there is a function that's just something raised to a power that has the property that the derivative of the thing is equal to the thing itself. So let's assume it's of that form, a to the x. Let's differentiate that with respect to x. We get this result here, and it says, okay, that's the symbolic result. But let's imagine that we were going to get, what are we going to do here? We're going to say, let's do the following. Let us plot a of x and the derivative of a to the x with respect to x. Let's plot that from x equals 0 to 5 or something. Yeah, okay. Oops, what did I do wrong here? Plot. Oh, I got to give it a value of a. Let's manipulate that for a equals, let's say 0.5 to 5. Okay, so the blue curve is a to the x, and now a is equal to 0.5, so it's a square root. And this curve here is the derivative of a to the x. So let's vary a, and we're changing a, and now we've got above 1, and look at this, they're doing their thing, and let's just see whether we can get these two curves for the a to the x and the derivative of a to the x. Let's see if they ever join. Oh, look at that. At value 2.7, the two curves are on top of each other. Okay, let's go back here. Okay, those two curves are on top of each other right there at value 2.7. So for a to the 2.7, roughly, the a to the x is the same as the derivative of a to the x. So looking at that in terms of this equation, we're saying f prime of x, the derivative of f of x, is the same as f of x. And we're asking for what f is that true? And it says that that's true when f is e to the x. Okay, what is that e thing? Well, in Wolfram language, it's just a capital E. And although it can also be represented as that exponentially, if we what out what's the numerical value of e to 50 decimal places, it's 2.718. This is the so-called exponential constant, lowercase e. It's in Wolfram language, you can represent it like that. And that thing is the number which has the property that it raised to a power has this property that the derivative of that thing is the same as the thing itself. That's the so-called exponential constant. Confusingly enough, Leonhard Euler promoted this constant, but it is not what's usually called Euler's constant. What's usually called Euler's constant is yet a different thing that's equal to about 0.577. That's a quite different thing. Euler's constant has to do with the sum of 1 over n, etc. It's a different thing. But it's always a giveaway that people didn't really learn their math history if they call E the exponential constant. If they call that Euler's constant, it's a mistake. It's not usually called that. Okay, so that's the story of E. It's the solution to the equation f prime of x equals f of x. There are a lot of famous differential equations. I mean, there's another famous differential equation. So this is basically saying the rate of change of a thing is the thing itself. So that's the more of something you have, the faster the thing will go. Or for example, we could say f prime is minus f of x, and then we get a result e to the minus x. or let's say we put in a constant here. Let's say we put in capital lambda just to be exotic. We'll find out that the function f of x is e to the minus x times lambda. So this is what, when we talk about exponential decay, we're talking about the fact that the rate of change of the thing is an exponential. The e to the doesn't have to be is we can write that as exp is e to the x, the exponential of x, and this is telling us if the change is minus the amount of stuff we have, then this is telling us how that stuff will decay away. Let me give you a couple of examples of this, and then we'll talk about logarithms and so on. But okay, so let's imagine that we keep on doubling something. So we take something and we're at every step we're doubling it. So let's say we start off with 3 and we double it and we double it again, we double it again, double it again. That's otherwise known as 3 times 2 to the power of, in this case, it's 2 to the 6. So, 2 to the 6, yeah. Okay. Okay, so let's say, so we can write that as a formula as something like 2 to the power t, let's say. And when t is 6, we get that result. But we can think of this formula as working for any value of t, not just a whole number that represents explicitly multiplying by the 2's. We can say 2 to the t for any t. And that will tell us that, so we can think of it every, let's say, every second something is doubling. And so it's multiplied by 2 every second. But we can say that means that it is, it's doubling every second, but we can say how far does it get after t seconds? And the answer is 2 to the t. And that's what happens in kind of a chain reaction, for example. Well, let's take a look at that. Let's say, let's see. We could do that with like a carry tree. What do we do like this? Come on. That's not what I want. I want to. Oh, I can certainly do this. Okay. This is kind of a representation of something that doubles. So, you know, from the 1 you get, it splits in 2. This happens in cell division all the time in organisms. It's like first there's 1 cell, then there's 2, 4, 8, etc., etc., etc. And so here we're seeing that in a series of layers. We're seeing it doubling. If we say, in this case, it's going 2, 4, 8, just doubling like that. But if we say, what's a version of that where we're continuously doing the same kind of thing, it will be like 2 to the t. And we could represent that as a differential equation by saying the amount that we're growing is proportional to the amount we already have. And that will give us this exponential. And similarly, we get exponential decay, like radioactive decay. Given that there's some number of atoms that are there, there's a certain rate at which each atom will decay, and the total number of atoms that we have depends on it goes down as atoms decay, but the amount that it goes down by is proportional to the number of atoms that are already there. So what we're saying, that's basically this equation here, f prime, the amount that it's going down is proportional to the number of atoms that are already there, but it's minus something because that's representing the fact that the total number of atoms is going down. Okay, let's talk about logs. So let's say we've got 10, we've got 100, we've got 1,000, and we know that 10 is 10 to the power 1. Let's just make a table. 10 to the power n where n goes up to 10, let's say. 10 to the 1 is 10, 10 to the 2 is 100, 10 to the 3 is 1,000, 10 to the 4 is 10,000, and so on. Okay, how do we get back that n that we get from this? So let's just say solve 10 to the n equals, let's say 10 to the n equals 10,000. Let's just solve that for n. Okay, oh my gosh, that's so complicated. I need to tell it that I only want the solution for this for reals. Okay, there we go. It was being very, very pedantic and correct. But here we say, for what n is 10 to the n equal to 10,000? The answer is n equals 4. Okay, we know that easily. For what n is 10 to the n equal to 1,000,000? Okay, it's 6. Okay, so now we could ask the question, for what n is 10 to the n equal to some number x? Okay, and the answer is, oh boy, that's represented in a very funky way. But yeah, I can tell it. Okay, but anyway, the answer is a logarithm. And let me show you. And so if I say log to the base 10, it's called, of, let's say, 1,000,000, the answer will be 6. So it says log to the base something b here. We'll say what power of b equals this thing here. Okay, so a very convenient base of logarithms is base log to base e, because if we have log to the base e, well, let's remember that we showed before that this exponential function with, okay, so if I take the derivative of 2 to the x, I'll get a big mess here. I'll get this mess with log 2. If I take the derivative of 3 to the x, I'll get that. If I take the derivative of a to the x, I'll get this thing here. So for what a is the derivative of a to the x just equal to a to the x? Well, the answer is for a equals e, the exponential constant, the derivative of e to the x equals e. And the same thing is true with the integral. If I take the integral of, let's write it this way, e to the x with respect to x, again, I just get e to the x. So similarly, so logarithms are just the thing you get if you reverse. So the log of e to the x is just going to be x. Oh, oops, I didn't tell it to. I have to tell it to simplify it because it isn't always. Let's see if I do this. Oh, come on now. How do I tell it to do this? Well, I can just tell it x is bigger than 0. Okay. The reason it's being persnickety like that is that there's some, okay, if I were to really, let's see, 2 pi I. No, this is what I want. Yeah. So this is just a piece of mathematical complexity that actually is related to a very famous formula, which is the e to the 2 pi I. Remember, I is the square root of -1. E to the 2 pi I is equal to 1. Or e to the pi I, the square root of that, is equal to -1. And that's a sort of a famous formula in math that relates, we'll write it out a bit more nicely here, e to the pi times I is equal to -1. It's a formula I can explain why that formula is true. But what was I going to do here? I was going to look at log, and I was going to look at log. Let's see. So one thing you could ask is, what's the derivative of log x? And the answer is 1 over x. So this is kind of a tricky case, because if I say, what's the derivative of x to the n with respect to x? The answer is n times x to the n minus 1. So you say, what about, what happens when n equals 0? This is maybe this is too complicated. This is sort of a corner case when n equals 0, because when n equals 0, this is like, okay, what's x to the 0? X to the 0 is just equal to 1. And so it looks like you're just finding the derivative of 1. But it's a tricky thing because you have to decide which quantity you're making small first and so on. It's a whole elaborate piece of math. Let's see what else to say immediately about these things. I wanted to explain logarithms. You can do, I mean, we can, what's the integral of log x? That is slightly more complicated. It's x log x minus x. We could say, we could work out something like the log of x, and we'll start getting much more elaborate kinds of things. We could work out the log of the log of the log of x. Now remember, we can't even do that as an integral. Although if we wanted to know, remember it's the area under a curve. So if we say the area from x equals 0 to x equals 1, grind, grind, grind. Can it do it? Can it do it? It's trying really hard. Maybe it's going to figure out a formula for the answer. Maybe. Nah, failed. But if I wanted to, I could say, what's the answer to 50 decimal places? And that's easy. It has a complex number piece, which is complicated, but that's not too surprising. All right, so anyway, a little bit more math. It's there's no, what else could I tell you about? Well, I can tell you there's a lot to say about, for example, differential equations. And differential equations, you can have really quite simple equations that have very elaborate solutions that kind of wiggle all over the place. And that's maybe, well, let's see if I can do that. What's a good example? You know, I could probably just type in an equation pretty much at random. Let's try and type in. I'm just going to live really dangerously, and I'm going to try typing in an equation pretty much at random. And I'm going to say equals f prime squared plus f of x. And I'm going to, yeah, by the way, that thing there, that double prime is the second derivative. So if we say, what's the derivative of x to the sixth, for example, with respect to x, okay, we get that result. We can say, what's the derivative of that with respect to x again, and we get that result. And we can, in general, we can say, we can do more and more derivatives. Why is that relevant? It's relevant because in a lot of situations in physics, several derivatives are relevant. So for example, if you have a position and you find the derivative, how is that position changing with time? That is the first derivative. That's like f prime of time. Then that gives you the velocity, the speed of a thing. If you take the second derivative, that's the rate of change of the rate of change. That's the rate of change of the velocity with respect to time. That's the acceleration. So it's pretty common to find lots of physics equations that involve two derivatives, because that's going from position to acceleration. That's saying the acceleration is proportional to something. Big fact from Newton's second law, that the acceleration of a thing is proportional to the force that's exerted on the thing. In more exotic situations, you deal with a third derivative that's often called jerk, how jerky the motion is, but that's much more exotic. There are many fewer equations that involve the third derivative. But let's go and let's try typing in an equation here with two derivatives there. I'm just going to, just to make it really exotic, I'm going to do this. And then let's say solve that. And I think it doesn't have a hope. If it manages to solve this, I'll be amazed at, oh, well, it almost solved it. Oh boy, it kind of gave us some homework to do. It said the solution is these weird integrals here. Okay, well, but what I can do here is I can just say I want to solve this numerically. I have to tell it the initial values of, let's say, f of 0 is 1, and I have to tell it f prime of 0 is, let's say, minus 1. Oops, minus 1 here. And let's see if I can solve that. Oh, yeah. I have to tell it. I need to solve it over a certain range. Okay, this is getting kind of, oh, wow. Told me this equation blows up in some horrible way. Well, that's what can happen in these things. Okay, there's a result, at least. Again, this is all getting kind of complicated. But this, remember we used that interpolating function before and I was just kind of scribbling things. Well, now I've got this interpolating function is representing the result of this equation, and that's pretty boring. Okay, that's the result of my equation. Okay, to make it a little bit more exotic, let us go ahead and let's do this. Let's do this because I'm trying to tell you that this, hold on a second. I'm trying to solve the equation and I'm going to put in something. I'm going to put an A in here and I'm going to just vary that A. I'm going to keep on solving that equation for different values of A. Let's say from -4 to 4. Okay, so now each time I change A, I'm going to be resolving that equation. Ooh, it went crazy here. I bet it started having complex numbers there. So every time I move this, I'm picking a particular value of A, and I'm working out what function F that I'm plotting here satisfies this differential equation. So things are getting kind of complicated here, but this is some kind of feeling for what goes on. I mean, if you were to show, wonder if I can pull this up quickly. Let me just show you. I wonder if I can pull this up really fast. Hmm. Okay. Well, I'm not sure if I can show you the equation for this, but this is like the Earth, Moon, Sun, and this is a collection of differential equations that are just like the ones I just showed you. They're just equations for the position of the Earth, the Moon, the Sun, basically, and we can solve those. And if I work out, let's see, if I do this. Let's say I call this data of my simulation. Again, these are pretty simple equations. I'm not sure if I have a way to show you the equations from this. We probably should have a way to do that. And is there any way to do that? No, there doesn't seem to be. Okay, but anyway, I can show you the result from solving these equations. And this is going to be the idealized Earth, Moon, Sun. And those are the results from the equations. And they're really complicated. And that's a pretty common thing for differential equations to see very complicated solutions. It's kind of part of the symptom of happens also with integrals. Maybe I should have plotted some of those results from the integrals that we got. Just to give you some sense of how things work, let me show you one more thing, which I might be able to show you. Let me see. Oh, got one thing here. Let me see if I can pull this up. When you represent all kinds of systems in engineering, they are represented in terms of differential equations. So let me try and show you an example of one. Let's see. Let me show you an example of, oh, I don't know what this is, but let's see. This is probably going to be super duper complicated. This is an electric circuit. This is a representation in Wolfram language of an electric circuit. And if I were to show you, just a minute, were to show you this, I can probably show you if I know how to do it. Let's see. There we go. If I were to take that thing and I were to say system equations, this is going to be a horrible mess. But basically, Oh boy, horrible mess. I told you it's a horrible mess. Somewhere here, if I dig through it, there will be little derivatives here. Well, I can't find them immediately, but somewhere there will be little derivatives, and these would be differential equations, and I would be, again, to work out what happens with this electric circuit, I would be I would be basically just solving now all kinds of differential equations and to get these results. All right, one last thing I thought maybe I'll do. Remember, we were looking back ages ago here. We were looking at some of these integrals that end up being pretty complicated. I just want to show, I'm actually not sure what this will look like, but let me kind of show you. There's some function here, and let me show you the plot of that function. X goes from, let's say, 0 to 10. Okay, that's a pretty boring looking function. Let's see whether the integral is similarly boring looking. There's the integral, and let's say plot that, x from 0 to 10. Ah, so sad. All right, let's see. I have a bad feeling that what happened is we need to do that. Wow. Okay, it got really complicated really fast. I mean, all right, forget that. This is not going to be easy to show. But it is true that this thing here, for any value of x, this thing will just give a number. So let's say I say x equals 0.5. This will just give a number. Yes, I was afraid of that. I was afraid of that. This thing here we're now diving into the horrible complexities of mathematics. This thing here, for any value of x, let's say x equals 0.5, this thing here is just an ordinary number. The problem is that when we give a formula for the result, that formula can involve complex numbers. And let me just show you roughly why that is. See if I can show you that. Yes, it's all to do with this famous result, e to the I pi 2I pi equals 1. Okay, well, if I say e to the 2 pi I plus x, that's, if I say full simplify that, it's just e to the x. So anytime I get a formula for something which was supposed to be e to the x, it could have some nasty 2 pi i's lying around as well. Well, that might not be too horrifying, but for the fact that if I take the logarithms of these things, I'll end up getting a 2 pi I in the logarithm. And I'm pretty sure that's what's going on here, that there are a bunch of loose 2 pi i's floating around that are still valid results for the logarithm, but which mess up kind of the way of representing this as a symbolic formula. All right, with that, I've descended into a level of extreme complexity. I guess I have a few minutes. I could try and take a few questions here. I see a whole bunch of questions. Let me try and I will upload this notebook, by the way, for anybody who's interested to take a look at it. Let me start off a questions section in case we actually are doing different things here. All right. Well, Technic was asking, where do the symbols plus, minus, times, and divide come from? Well, they're from the I think the 1400s. Plus and minus came from the 1400s, times from the 1600s, the division symbol about the same time. When the times sign was invented, a chap called William Outred, I think, invented the times sign. Gottfried Leibniz, who was a big enthusiast of notation, although he invented some notation that's confused people for 300 years himself, said to Outred, don't use an X for this multiplication thing. Everybody's always going to get that confused with the letter X. But the world doesn't always pick the right thing, and so now we have that times sign. There are a lot of different notations. For example, one notation that is the notation for greater than, x greater than y, or something like that. Leibniz actually had a very nice notation for that, which looked like a scale where you could be pulled down on one side or pulled up on the other side and so on. And it was kind of like that was his notation for what's greater than what, is what would be further down on the scale. And instead of an equality, he had this thing where the scales match. The equal sign was invented a bit later. Let's see. Nato was asking, is square root of 3 a real number? Yes, it absolutely is a real number. Let me just share again here. It's the square root of 3 is a happy real number. It has some, you can work it out as much as you want. It is not, if I took that number and multiplied it by itself, let's take that number and multiply it by itself, we get basically exactly 3. So it really is, that is the square root of 3, except it goes on, it has an infinite number of digits if we really wanted precisely the square root of 3. And that's, if it was something like the square root of -3, it would get more complicated because there's no number that when multiplied by itself, there's no real number that when multiplied by itself gives -3, but I times square root of 3, where I is the square root of -1, that when multiplied by itself gives -3. But the tricky thing about square root of 3 is you might say, well, can I take a number which is just something divided by something and have that be square root of 3? The answer is no. That was a thing discovered by Pythagoras that, among others probably, that there is no rational number. If I say, give me a rational approximation to this, I'm not even sure it'll be prepared to do it. No, it won't be prepared to do it. If I say, give me a rational approximation that's really close, that number there, if I work that out numerically, that will be pretty close to the number that I have for square root of 3, but it will never be exactly square root of 3. There is no rational number which is the square root of 3. So it's a different, there's no, if we write it down in terms of digits, we can never specify, we'd have to specify an infinite number of digits to say exactly square root of 3. Let's see. You guys are asking sophisticated questions here. What determines the cases for which integrals come out in terms of known functions? Really, that's a lot determined by what known functions we have defined. I mean, that is, as I said, there are about 400 of these things. We can go and look in Wolfram language documentation. It's kind of the world's most complete collection of these things, and it would be in here, and it would be in oh, it's probably in here. Okay, let me make this bigger. Okay, so here are some members of the zoo. I mentioned the gamma function. It's a generalization of the factorial function. There's the Bessel function. These are elliptic functions, Legendre functions, Chebyshev functions, the hypergeometric functions I mentioned before. There's a whole giant zoo of these things, hundreds of them. And these are functions that have been found useful in human mathematics. They're not the only functions that one could find useful in human mathematics. There are a certain set. And when the calculation you want to do, the integral you want to do, lands in a place that's familiar, where other people have defined that function before, then you're a winner, and you can think of it as a reducible kind of thing because it is something that attaches to a known function. What is not obvious is that if you scan across all the integrals you want to do, that for lots of integrals you want to do, you will be hitting, for the integrals, you will be hitting functions that people have studied before. That might be the case, it might not be the case. As we started looking at integrals, when I did that just a little while ago here, some of the integrals that we looked at did have did land in the domain of functions that we've looked at, that people have defined. Other integrals didn't land in that domain. Now, if it turns out that people were super interested in integrals of some particular form, they might define a function that represents those integrals, and then we'd be back to thinking that this is a thing that we can represent. In the more general theory of computation, it's like saying you have some particular model of computation, and there are certain primitive operations in the machine that you're using for computation. And if the thing you want corresponds to one of those primitive computations, the computation will be easy for that machine. Now, what is true in general is that there will always be computations that are hard for any given machine. The same is true of integrals. In fact, the same results about fancy stuff like undecidability occur for integrals. And essentially the reason for that is, well, gosh, the reason for that is it's very hard to tell if you have, let's say, I say square root of 2 plus square root of I don't know, 7, 6, whatever it is. And now I say, that's not a very good answer. Okay, let's take a look at that. This is not a particularly good example, but there, in general, just as there are many different forms of an expression like x squared minus 1, so when you have expressions that involve square roots and so on, there can be many forms of those. When one's dealing just with square roots, there's a definite procedure for figuring out whether two square rooty expressions are the same, even if they're written in a different form. So, for example, I could probably, if I write this, let me just see if I can, by hand, come up with an example here that can be written in multiple forms. I would guess that if I say square root of 12 there, it already did it. Well, anyway, for square rooty type things, there is a definite procedure for always unwinding them. As soon as you have things like pi in there, that's no longer true. You can write expressions that involve square roots of pi's and things like this, where in general there will be no finite procedure, no known procedure for telling whether these two expressions are equal. And that particular phenomenon kind of bites you in working out integrals. And in general, that means that you won't even know whether integrals of a certain form all lie within a region, so to speak, that corresponds to a particular function you've named. So that's the general way that works. Let's see. Somebody noticing, Joshua noticing that I make the same mistakes as they do. Yeah, well, we're all human. We try to, in developing Wolfram language, we try progressively to make it sort of harder and harder to make mistakes. But the one I made was a conceptual mistake. And maybe if I'd been talking to an LLM, and that's a capability that we have, I would have been able to have a discussion, and it would have kind of pointed out some of the things that I was doing wrong, or I would have understood from that discussion, Socratically, so to speak, that I was doing the wrong thing. By the way, I should say, how do humans manage to do integrals? Well, I have to say, I haven't been doing integrals. I almost never did integrals by hand. I started using computers to do integrals as soon as the integrals I wanted to do were at all complicated, back sometime in the mid-1970s. Although even when I was doing them by hand, I'll tell you a sort of shocking fact about my life as a human integrator, which was that I learned certain formulas, and I alluded to one of them involving those gamma function things before. I learned certain formulas, which are very general formulas for doing integrals, and a vast range of integrals that one might need to do things in practice or to do things for exercises or whatever, one could do with those formulas. The problem was then grinding those formulas to make the answers sort of plausible, and the answers sort of be be things that were recognizable, had pieces that were readily recognizable to people. That was the challenge. But I kind of learnt to do integrals as a human in the same kind of way as later we taught computers to do integrals, by using these kind of industrial strength methods and so on. Now, I will say that one feature of doing integrals is once you've guessed the answer, you can always differentiate. If you've got various parameters in the answer, you say, oh, it's going to be a times this plus b times that plus c to the power of that and so on. If you know the form that it might have, then you differentiate that answer again. Then you get something involving a, b, and c and so on. And then you try and sort of match that up and solve the equations for, well, what values of a, b, and c would you have to have so that that derivative that was supposed to be the thing you started from actually is the thing you started from. And so that method is one that one uses all the time in trying to get computers to do integrals when one isn't just using these kind of industrial strength formulas. And that phenomenon of if you can guess the general form of the answer, you just have to differentiate it and match up those coefficients and so on. That is a method that I started using as a human to do integrals with the help of a computer often to do the derivatives and so on, back in the 1970s. And it's sort of an interesting thing because it's something where if you are trying to have a machine learning system, that's the kind of thing a machine learning system is plausibly able to do. It's able to say, gosh, here's this integral, like for example, I can tell you, we could do a little exercise here. If you give me an integral, okay, so I could tell you, if you say integrate e to the x squared, okay, I can tell you that's going to come out, well, let me put some extra hair in it. I can tell you that's going to come out in terms of an error function. Okay, there it is. It's an earth. I knew it was going to be an earth. I didn't know if I had known. So let's say that I knew it was an earth. That earth I is a slightly complicated thing. I'll put that in anyway. Let's say I know it's a times x plus b, and then that whole thing times c. And now I can say, let's differentiate that with respect to x. Okay, well, there I get the result. So look, I've got b plus a all squared there. And so now I just have to say, well, what would I have to put in there to get this result here? So to match up with e to the x squared plus x, what do I have to set a, b, and c to be so that these all match? Okay, so that's kind of a way to do integrals. So you give me another kind of integral, like for example, if you give me log 2 plus x over x plus 1, I think that's going to come out in terms of the log integral function. I'm wrong. Oh my gosh, how could I be wrong with this? That's one of my favorite functions, the dilogarithm function. Oh my gosh, I'm so embarrassed. Let's see, I would be, let me think. Is this what I want? No. Now I'm really embarrassed. What is the derivative of the log integral? Oh, that's right. That's right. That's right. I'm rusty. I'm out of practice here. Okay, so but this is my actually all-time favorite function. It's a slightly obscure function. It shows up a lot in the computation of Feynman diagrams and quantum field theory. But like, for example, if I were to give you, think if I were to give you log squared here, what would that do? Yes, that gives a trilogarithm function, a polylog of 3. And so that's another, if it's that to some power, it's a polylogarithm function. Or for example, I think if I were to give 1 over sine x plus 1 plus pi or something, then I think that's going to be a sine integral function. I'm wrong. Really? Oh gosh, that's obvious, isn't it? Yes, maybe it's, well, I'm thoroughly wrong here again. Again, so you see this is, oh yes, okay, So then if I were to do an integral, oh, that's right, sine x over x, then I would get the sine integral function. And if I were to embellish that. Let's do an e to the x. Well, I wonder what this is going to be. That might be an array function. Ah, we can't even do it. Well, let's get rid of the over x. Let's see what that is. I'm kind of thinking it might be an array function. Really? Huh. Odd. Well, actually, let me try another one. Yeah, let's try e to the x cubed. Okay, that might be an array function. Yeah, I'm pretty sure that is an array function, although not stated in its usual form. Oh, look at that. We went from a gamma to an x integral e function back to the gamma function. I think that gamma, that's an incomplete gamma function, and I'm pretty sure that's an array function. Anyway, there's a giant zoo of these things, but the main thing that's sort of interesting is to get an intuition for what kind of functions are likely to show up for what kind of integral. Now, the fact is we've tried using machine learning for more than a decade, trying to do this and trying to get it to really do well relative to kind of our industrial strength methods. We haven't succeeded yet, but it's a place where it's sort of plausible. There are lots of kinds of computations where it's completely implausible. It's something like a neural net will be able to do them. But this kind of guessing of what's a possible form for an integral is a case where I think one can make progress there. Let's see. Well, should probably wrap up here. Yeah, it is fun. I mean, just sort of at a meta level, what I have been doing here is kind of, here's what you can say about math that was built up over the last few hundred years from the vantage point of modern computation and our modern computational language. And, a lot of things that were extremely hard won in the actual history of mathematics are now trivial for us. And that's true not only at the sort of level of the mechanics of working out computations, it's also true at a conceptual level. For example, the notion of what is a function. Well, in Wolfram language, it's easy to understand that. It's a thing f, you can give it an x blank and you put anything into that blank spot and it transforms it in a certain way. That's a pretty easy to understand thing. The way functions were first understood, and it took a couple of hundred years to sort of gradually get understood in the history of mathematics, was much more complicated than that and required much more conceptual apparatus to kind of see what this notion of a function is. And it's much more abstract, as it's usually stated in kind of a math textbook. It's a mapping from a space to a space, from the real numbers to the real numbers, things like this. You don't need any of that. As far as all of this treatment that I was giving you, which was real life calculus and so on, this wasn't, this was not dumbed down, so to speak. This was, calculus as it is seriously practiced, so to speak. And we were able to get to that without having to introduce a lot of the kind of conceptual baggage which was needed in the historical progression from the 1600s to today, but which now, from thinking about things in a computational way, we just don't need that baggage anymore. We can really go from this kind of very structural concepts right to kind of how the calculus kinds of things work. So that's a thing it's really a very powerful idea, which I don't think people have really taken advantage of yet. That the sort of computation and computational language is not only a way of, in practice, doing your integrals and so on, it's a way of understanding the whole idea about what's going on. And that's true all over the place. Now, I will say that calculus and its whole treatment of, well, what happens if we make an infinitesimal change? We're asking, on these curves, we're asking, what's the slope of this curve right here? And the curve, we might say, well, it starts off pretty flat and it gets to be, going up much faster. But yet we're asking, what's the slope? What if we took a if we took a line and we just sort of put it up against the curve, what angle would it be at when we put it up against the curve? right at that point, at that infinitesimal point, so to speak. And that's and this idea of sort of what are things like at infinitesimal positions and so on, that's a key idea of calculus, the whole dx business and dy by dx and integrate dx and so on. That's all talking about sort of infinitesimal distances. Now, a little bit of I would say, not really a downer, but a thing to mention is that in the theory of physics that we've developed in the last 5 years or so, it's pretty clear that space isn't continuous like that. But it isn't true. I mean, for Newton, for example, he just assumed that you could specify a point in space, and it could be anywhere. It could be specified by any number. Descartes had come up with kind of the idea of coordinates. You can specify a place in space as represented by 2.7384, some long sequence of numbers. That's the place. Okay, so, we know lots of things are discrete. I mean, if you were looking at I don't know, a diamond crystal or something, which has all those carbon atoms all lined up in a very precise way, and you wanted to say, I want to say which atom is at that particular position, specifying it to any number of digits. There might just not be an atom there. There are only a discrete set of possible positions at which there is an atom. And we're pretty sure that's how space works as well, except it's not something like a rigid lattice like that. It's a more complicated structure involving networks and things like this. But so that means that this idea of calculus, where you're going in and you're saying, I want these infinitesimal distances, it in the end isn't going to make any sense because there is a shortest distance. There is an elementary length. It might be 10 to the minus 100 meters. It's very small, but there is an elementary length. So where does that leave calculus? Well, part of where it leaves calculus is that for us humans experiencing space, it seems continuous to us. We can move continuously from here to there. If we were on a computer screen and we were looking at our image as pixels, well, we wouldn't move continuously. We'd move pixel by pixel. But for us, the way we think about things, because of the way that we sort of interpret things internally, it's as if things are sort of continuously moving from here to there. And that's what calculus represents. Calculus is a way, at least, of representing what we think of as our inner experience of things like space, this continuous change and so on. Even if it's not what's actually going on, it's a good approximation that we can use to understand what's happening. And so that's sort of the value of calculus. Now, I will say that in practice, calculus has been much used in recent times in machine learning. It's a very convenient way to kind of package up what sort of, the reason you care about small changes in machine learning is that if you are trying to teach a neural net something, you say, okay, neural net, you're set up in this way with these particular numbers, these weights in the neural net. What do you think this is a picture of? And you showed a picture of a cat and it says it's an elephant. And you say, no, it's not an elephant, it's a cat. Move more from the elephant position in your results to the cat position in your results. And you want to sort of make a small change from elephant towards cat. And as you make that small change, as I mentioned, it's kind of, you get to use the chain rule to sort of propagate backwards. To get that small change to happen, how would you have to change these weights and so on? And that becomes, at least in terms of the way the formalism is set up, really a thing that is represented symbolically in terms of calculus. So it's sort of a place where calculus shows up. Now, actually, just a few weeks ago, I wrote something about how one can do machine learning using discrete systems, and I think that's very promising. And that won't directly use ordinary calculus. There's kind of a discretized analog of calculus that you can start to use. I might say, by the way, when you're starting off from these networks that represent the underlying structure of space, and you're building up everything from that, there's a new version of calculus that we should be able to build, not for things that are like ordinary space, but for things that emerge from having a large number of nodes, a large number of points in these graphs. The emergent analog of space will have a new kind of calculus. And one way that shows up is in ordinary calculus. I was showing you univariate calculus, calculus of one variable. You have a function and you're making a change, you say f of x, you're changing x, you're finding the derivative with respect to x, you're finding the integral, you're finding the area under that curve. But what if you have a function of two variables, f of x and y? So that's like having a value not at a position on a line, but any place on the plane. So you've got f of x and y, and you can start asking not what's the area under the curve, but what's the volume of the surface that you get by plotting with height f of x and y, f of x, y, what's the height of that? And there's a lot of more elaborate, I'd be happy to talk about it sometime. People are interested. Multivariate calculus, that's another course in the sequence of calculus courses, which I don't understand how that sequence works. But anyway, there's these multivariate calculus is one of the things you do after you do ordinary calculus. Multivariate calculus deals with the considerable, well, there's some extra complexity in dealing, and there's a lot of extra nice things you can do when you have a function of several variables and you ask not sort of what's just the change with respect to one variable, but sort of what direction takes you most down the hill. If you're plotting, f of x and y is plotted as sort of a height of a hill, what's the gradient vector that takes you down the hill and so on. There's a lot of interesting stuff there. But multivariate calculus is a function f of x and y where there are two variables, three variables, whatever, some number of variables. What we need for the limit of these hypergraphs that we're looking at that we think fundamentally represent space is not a function of one variable, two variables, three variables, but basically a function of fractional numbers of variables, a function of 1.5 variables. And that's a thing for which there is no existing mathematics, basically. And so we've had to start building that mathematics, and it's pretty cool. And what I think is interesting, and maybe in a few months or a year, maybe I'll be able to give you a discussion like the one we've just been having here, but in terms of what we're calling infracalculus, the calculus that you get by doing these things that are below the level of things like real numbers and continuous variables and so on. And I think infracalculus might be easier to learn than ordinary calculus. We'll see, even though in the end, the kinds of things that happen in it are considerably more complicated, but I don't know that yet. Okay, we're getting one vote for a multivariate calculus stream. All right, I'll try to do that at some point, hopefully before we get to another math storytelling day. Well, okay, this was very educational for me. I hope you guys learned something from it. It's educational for me because I said I never taught a calculus course or anything like that. I think I understand calculus fairly well, although as we saw close to the beginning, there were things that I got tripped up by. But in any case, I think I understand it fairly well. But this effort of trying to explain it without making other assumptions is really an interesting problem for me. And it was great to have a chance to try it out on all of you. So thanks very much for joining me. And we will upload this notebook. And I'd like to point out, if you want to play with these things, actually, I'll say two more things. That, get a copy of Mathematica or Wolfram Language or use it in the cloud, play with all of these things, get a sense of, get your own intuition about integrals. People think of integrals as just something you have to grind through one by one, but when you do them kind of on a large scale and you kind of, pretty interesting to try and get intuition for what will happen. It's one thing to say. Another thing to say, our Wolfram U education unit has produced recently an actual calculus course, and it even has a book that goes with it. And it's freely available on the web, and the book is, I think you can actually get the physical book now, and that's making use of all of the kind of technology that I was showing here to explain calculus in a comparatively traditional way, but with the extra clarity that I think this sort of explicitness that you get from being able to do these computations so easily brings. Anyway, I should wrap up here. Thanks very much for joining me, and talk to you another time.